So I think we'll get again. It was a very good question before the break that we're great to get the Curtis's 2 cents on, which was Gerardo's question about using essentially a thermal gradient in compositional gradient calculations in general. Bilal touched upon a few key kind of takeaways from that on that topic. But Curtis, if you can shed some light on your discussions with and dialogue with Mikkelsen and potentially others on that topic, that would be great.
Right. So the isothermal chemical gravity model that predicts compositional variation with depth under the assumption of a constant temperature is the only rigorous thermodynamic model that exists. It's founded in all of the fundamental thermodynamics laid out by Gibbs. When you go to a system with temperature gradient with thermal fluxes, all thermodynamics basically disappears, the formal thermodynamics, and you end up with pseudo thermodynamic concepts that are physical, but they're not well defined theoretically. So all of the models out there in different programs for including temperature variation with depth, as in PVT SIM and other programs, they use different models to introduce flux of components due to thermal gradients, as well as gravity and chemical potential. So they solve a set of equations with a set of assumptions that are not really rigorous. And there's a number of models, there's a number of ways to do it. Many different models have been published. There's examples showing calculations that are going the opposite direction in terms of the effective thermal gradient being to increase gravitational segregation or to decrease segregation due to gravity. So what's in any given model with temperature variation with depth is an empirical heuristic model. Mikkelsen, once I asked him, his take on the best approach to modeling compositional grading with thermal temperature gradients. Mikkelsen is kind of the godfather of rigorous thermodynamics and computational methods. He said, I stay away from it because any model that depends on an arbitrary choice of reference conditions and properties is not worth messing with. Basically, you don't know whether the answer is going to be right or wrong. You can always, tune such models, but you can't use them predictably. So that's my take on it. There are other effects that are usually neglected when doing compositional grading that have been shown, even for the isothermal case, to have a much bigger effect on gradients than thermal, and that is namely to include the aromatic compounds as separate components in the EOS characterization because they have such a pronounced effect on gravitational segregation. That's not that approach of having different pseudo components that are aromatic and paraffinic and whatever. It basically is no longer used by anybody, certainly not in commercial software. That averaging of single carbon number, averaging paraffin, naphthene, aromatics into single carbon numbers can lead to errors in calculated isothermal gradients that are adding the thermal term is just kind of a joke afterthought. This I've tried to bring up in open discussions in the industry with people like CalCEP, and they kind of boohoo it and say what we have is right. So at the end of the day, my take on it is that if you believe thermal diffusion transport is important, then use some model. Don't say it's right, but get measurements or data, tune that model to measured, observe compositional variations with depth, and just basically be happy that you have an extra knob or two to turn to get that fit of the measured variation with depth. But just realize there could be other reasons for the measured variation with depth other than the thermal treatment that you're tuning with, because you're ignoring other effects. So it's basically a non-unique problem. Adding the thermal term makes it appear to be better. I think you could collect 10 or 20 thermodynamists from around the world and have a discussion on this, and nobody would agree with anybody, I think, at the end of the day. So, yeah, thermal effects, thermal gradients can cause component segregation different than gravity. Yes, but we really don't have a model that predicts that a priori. You have to tune those models and be careful with them, just like dips.
Yeah, thanks, Curtis. This has been very relevant in two wells I've been involved where we thought we were close to the contact, and then of course it becomes a matter of how much volume of oil you have, if you believe you have a gas cap or not. Yeah, and it's very
well. There's a classic example. Actually, I programmed up a thermal term in PVTX way back. It was actually Paul Bellery from Petrovina, who it was his model, and I think it was in the late 80s, maybe early 90s. I got a phone call from Sheng-Tai Li, who was the PVT EOS specialist for BP. And they had this discovery well in the Cupiagua field in Colombia, which is a billion barrel gas condensate field, and its sister field, Cusiana, which is a oil and gas field. I got a phone call from him and said that, well, the first well came in, it was literally 6,000 feet thick section. I'm not talking about top to bottom dip, but it's like you drill through 6,000 feet. And the first well, and it was expensive, complicated drilling, is kind of a very tight, but fractured, tectonically fractured sandstone. And they drilled the first well, and they got a near critical gas condensate through about 250 barrels per million at the top of the structure, or not structure, the top of the formation. And it was somewhat undersaturated. So he did the isothermal compositional gradient and predicted a gas oil contact, I don't know, maybe 500 feet deeper. Okay. And it put about 4 billion barrels of oil in place based on their volumetrics with that gas oil contact. So they drilled the second well, and they completed deeper in the and did the testing of that well. And they got, I think it was 1,000 feet deeper, and they got exactly the same fluid, 250 barrel per million gas condensate. So they should have been, according to his calculations with the isothermal gradient, they should have been into the oil zone. And you can imagine what management, because, you know, if you didn't have any oil at the bottom of anywhere in the 6,000 foot section, you had maybe 1 billion barrels of condensate in solution, and this original GOC prediction gave us 4 billion gave them 4 billion barrels in place. And so when that second well came in, they were not happy with him. And so he called, and he knew I had this in the software, and we went down and spent a weekend in Dallas together. I drove down from Oklahoma City, and he came out from Houston. And we did the calculations with this non-isothermal model. Basically, we had 2 points, and he wanted to make predictions of a new gas oil contact with the thermal gradient. I'll model I can give you a gas oil contact anywhere you like. And I said, but my name is not going on the report that you send to management. And sure enough, after they developed the field, they drilled all the wells from top to bottom, totally uniform composition, 250 barrels per million gas condensate, 1 billion barrels in place. So yes, it can have a big effect on the predictions of where there might be oil, there might not be oil. So that's a long story for the record, but yes, you can include a thermal gradient. You can get gradients. You can take away gradients as you like, but you basically need data and more than 2 points to fit to that type of model to feel like it's going to predict upwards or downwards. So.
And Curtis, I think you can also add comment. Like generally, we also recommend that if you have good data measured with depth, composition data with depth, we generally recommend to use the data as is without any model, and just use the model for extrapolation. And then there you just do the sensitivity, having a pessimistic and an optimistic case.
Yeah. So, I think, if you're on board with CalCEP and you have a single well, you want to do calculations and you want to map the uncertainty, I would do one where you just assume your first sample is constant throughout the formation with depth, no variation at all, as one scenario. I do the isothermal gradient calculation as another scenario, and then you turn on their non-isothermal temperature gradient model, and you get a third scenario. And what you're obliged to do is to run all your models, do all your in-place calculations of stock tank barrels and standard cubic feet with all three scenarios. And you give 3 numbers to the management, 3 sets of numbers, and not one. And if it was me to say which one is our base case most probable, then based on my experience, I would say if it's a non-fractured reservoir, I would use the isothermal gradient as base case. If it was a fractured reservoir, I would use uniform composition as a base case. And so those are recommendations. But as you get more and more data with depth and map out the variation, it's definitely better to use measured variations, do interpolation, do drawing of, the problem is that you have got 42 components in your EOS and you need to have a function with depth at 42 components. It's not an easy task. So using measured data, interpolating between those is a recommendation when you have enough data. That's right.
Very good. Did you have a question or comment, Hans Christian?
Just a short one. I heard that since we are using PVT SIM and the SRK has BIPs set to 0, Curtis recommend not to use BIPs with a 0 value. And I think many people using the plus regression when they're doing a tuning of the equation of state. Will you not recommend to using that plus fluid regression when you are just adjusting the molecular weight or the plus fraction of your molecular weight and just go directly to do something with the BIPs?
Well, yeah, I mean, I've not used PVT SIM for EOS modeling myself or developing models, so I don't know what all the options are for using BIPs as regression variables. You have to be careful no matter what software you're using with BIPs as variables. But yeah, I mean, I would certainly have BIPs as variables. I would have individual sample average molecular weights as variables in PVT SIM. That's the only way to, I think, change composition as a variable within the limits of experimental uncertainty, and probably using both it wouldn't be either or. I'd probably try to use both and see what, with minimal change in the tuning, gave the best description of all the PVT data. So it's not an either or thing. We generally have both small BIPs for SRK, smaller BIPs for SRK, non-zero. They might end up being zero for the hydrocarbons in an EOS tuning model, but it's seldom we see it. But they're definitely smaller in magnitude than Payne-Robinson. But yeah, using the BIPs and using this plus option, which is changing the C7 plus or C10 plus molecular weight to change mass to molar conversion. I don't know. I think it's not either or. It's probably would use both myself. So.
Very good. And actually, EOS tuning is going to be the topic for this next presentation. And here we're going to go through the general workflow of field-wide EOS model development. One thing I just wanted to do quickly before we do that is just because there's been a lot of name dropping this week of different folks that for some of you are probably very familiar, at least internally here at Whitsun. It's more like our grandfathers, I guess. But for those of you who haven't heard about Standing, Mikkelsen, and Keith Coates, which has kind of been the three names that has come most of the time this week, just to provide a little bit of context. There we can start with I guess the oldest one, which will be Standing, and he, for those of you who went to NTNU in Trondheim, he was actually one of those who helped found the petroleum engineering department here in Trondheim, Norway, before he went to Stanford and became a professor there, where actually one of his students was Curtis Whitson, and if I'm not mistaken, he recommended Curtis to go to Norway because there was a lot of exciting things going on there in the oil industry. And Curtis moved to Norway, and then through the years he got to know. And Standing was kind of like he was like a go-to person on PVT, I guess, in the world at that time. He had written a very popular book. He had a lot of correlations to his name, and then through the years when Curtis has been active, he got into contact with Keith Coates, which is kind of like the father of compositional reservoir simulation, and Mikkelsen, which is kind of like the godfather of thermodynamic or computational thermodynamics. And Keith Coates is American, Standing is American, I think, and Mikkelsen is Danish. And Curtis, you are American, but also a little bit Norwegian, I would say. So that was just to provide a little bit of context on the names. Very good. So in this particular section, we'll try to, the last presentation was very fundamental and related to the theory, and now we're going to go through how are we actually creating these equations of state in practice. And I guess essentially the recommended workflow that we've kind of converged to, or Curtis and the rest of our colleagues here have converged to after 30, 40 years with the EOS model development for fields all over the world. And there's going to be a short introduction, and then we're going to go through the comprehensive model workflow. We're going to go through different QC checks of the EOS model. So we had on Tuesday, we went through different quality checks for the laboratory PVT experiments, and we create an equation of state tuned to the laboratory experiments. But then once we have a quote unquote final equation of state, we need to also make sure that that equation of state is thermodynamically reasonable and physically makes sense. When you've created your detailed equation of state, that's the one we've Bilal showed on in the software that we'll use tomorrow. You might also, mainly for reservoir simulation, want to lump that equation of state into a pseudoized version or a lumped version. So we'll define and look at what that is and what that involves. And on a generic basis, you need that kind of reservoir or equation models in your reservoir simulator to save computational time, and for very, very compositionally sensitive processes such as for instance, modeling gas EOR, gas enhanced oil recovery, that we'll get to tomorrow. Maybe also some cases of gas condensate. Good. So just the first question that we like to ask people: if you have a field with multiple wells, and I guess the extreme case would be some of the unconventional wells that we have in North America. Take the Permian, for instance, where there's like, I don't know, 500-600 different companies, and several 10,000 wells drilled into the same reservoir. And if you were a company there that had 100 wells, but only 4 of those wells you had PVT data for, and you actually went into the field and developed an equation of state model for each of the wells, which equation of state model should you then use for the 96 other wells? And it can be very hard and not also very practical to actually pick what equation of state should be used for different wells. And it can also be very time consuming. And as we'll also talk more about it, it might not even be very consistent. So the solution to this is to create a field-wide or a basin-wide, or sometimes even called multi-sample or common equation of state model, which is an equation of state model as the one that you have in the software, the one that we're going to tune today together, where the 2 tables that we talked about, so the component properties and the binary interaction coefficients, the BIPs, those 2 tables are fixed. So we've done a good job, we've done all the tuning, and what actually changes from one well to another, or from a point in the to another point in the reservoir, or also through time when we produce different well stream compositions at surface, that is the compositions, okay? So you can actually have a field like we have in the Eagle Ford in the US, Permian, Montney, Duvernay, I think Vaca Muerta is the same, where you have one set of tables for the entire basin that you use all over the basin, that captures the relative paraphenicity and aromaticity that you find in these basins, which, if we showed you an example of that, it's very, very consistent over very, very large areas. And what changes from one well or in location to another is the composition, and also, potentially, or most importantly, probably pressure, but also temperature. Here's just an example of different type of fluids, where from what we learned the first day, this is probably this is a low shrinkage oil. So this is a black oil, and how we see that is from the more or less linear trend right here. Then we have a volatile oil right here at the top, and that we see from the little bit of bend in the curve right here. While here we see a very, very, very near critical gas condensate fluid, all predicted with the same equation of state model. And there are multiple examples of that, and that's what we're going to talk about today, taking not only one sample from a field, but all the samples that you have available in the field: separator oil samples, stock tank samples, multiple reservoir fluid samples from maybe different points in time as well, and create one model. And that's relevant if you have a field, as we talked about yesterday, where you might have commingling either topside, as was a question from Gerardo, tapping into several different fields and satellite wells and fields offshore as well, or if there's actually a commingling in the reservoir. This is relevant. Okay, the strict definition of such a equation of state model is that the multi-sample equation of state models is defined as each sample is described by the same model, where each sample's unique composition is all that is required to accurately predict PVT data for that specific fluid at a certain pressure and temperature. And then a question that always comes up is like, okay, but when do we actually? Why isn't there then one equation of state model for all fluids in the world and all fields in the world, and what is actually different from one basin to another. And that's what we spent a lot of time talking about on Tuesday. We touched upon it yesterday. We're going to iterate on it today, which is related to the C7 plus characterization. And it's how we average these heavier components, typically heavier than C7 plus or C10 plus, that can be radically different from one field to another. So, for instance, the donut field that Curtis talked about that was very aromatic and had a Watson characterization factor of close to 10 would have a very, very different C7 plus characterization than, for instance, the Permian or the Eagle Ford, which has probably a characterization factor closer to 12. And what's different between different fields is how we average these heavier components, where the heaviest component is actually, for instance, as in the PVT reports and equations of state we're going to use in this course, also in the software, is the C26 plus can be radically different from one field to another, where that kind of heaviest pseudo component is kind of like an average C30 plus or C26 plus or C36 plus for a particular basin. Okay, this slide is a little bit text heavy and not very I guess presentation friendly, but there are several scenarios on when we actually need a field-wide equation of state model for our engineering purposes, and different benefits from it. Compositional gradient, as we just talked about right here earlier today. We also have commingling in different reservoirs, either bottom hole or at surface. That was what we talked about also a lot yesterday from Gerardo's question right there. And then a thing that is also nice about having several different fluids is that the fact that a large database of fluids is a good QC model in itself, you avoid the potential overtuning of one fluid, while actually taking into account how that tuning process would affect, for instance, a gas condensate or a linear part of your fluid system. So it actually helps you including more data into the tuning model to create a more robust equation of state model. The common challenges related to developing these multi-sample or field-wide equations of state models is that you need to have a PVT package that has a very fast and reliable regression. And that's because when you're dealing with, like Singh, one of our colleagues here, and also Bilal, but Singh did, for instance, the Permian equation of state, the joint industry project that we've done the last couple of years with 12, 13 companies, and there it was 130 different samples that you had to regress on at the same time. And then back to Hans's question there earlier, there it was regression on composition within the uncertainty of that measurement, but also the binary interaction coefficients ramping on TCs and PCs and whatnot. So that requires a appropriate package to deal with that. So that's both on the actual component properties, these two tables, and the actual compositions at the same time. And to allow for that to be the case, you need to allow for small compositional adjustments, which for most practical purposes would be what Curtis talked about, which would be the small adjustments to molecular weight of C7 plus, which affects the distribution of the heavier components, and also the recombination ratio, so the vapor mole fraction that you recombine these fluids that you actually are measuring in the lab to what is then to be in the PVT cell. Yeah. From a high-level perspective, the workflow is first of all to obtain all the raw data. That can be either in a physical printed format, but more modern reports will be either in PDF, Excel, or both. from typical laboratories like ResLab, which is now Stratum, or Schlumberger Core Lab, and there's also multiple more options in that on that front. The second thing is to create a database of all that data to make sure that you get an overview of the data that's in the different reports, and very importantly, differentiate between what is actually calculated in these reports and what is actually measured, because you would like to tune. If you're tuning to what's calculated, you're just tuning towards a correlation. So you should be very aware of what's calculated and what's measured. And then it's also very important to do a very rigorous data filtering and quality control work, and that's probably where we spend the most time on or most of our time is, or at least a very good chunk of time, to make sure that the data that is categorized as bad quality data is not weighted during the regression, and that's an also important thing to just mention on that point, is that many times, which is very sad, is that we see companies, for instance, throwing away very expensive reports and just from PVT laboratory reports just because there was like one of the experiments had a material balance issue, for instance, or like there was something with one of the experiments that wasn't wrong. And what we always do is always to include all the data in all the reports, even the bad quality data as well. But then when we come to the regression part, we simply just don't weigh it, so it will not actually have an effect on our tuning of the equation of state. And then the question is, how do we actually develop the EOS model? That's what we're going to touch base on now with Bilal and whatnot the next hours. But in short, there's a lot of know-how and experience that goes into that. That's it's the same as people that's very very skilled in history matching a reservoir simulator. They know what knobs to turn. But there also has to be a focus on what at least we internally are very focused on is thermodynamic principles and these physical constraints that should be honored. Monotonicity in terms of the single carbon number, viscosities, and densities, and for instance also to avoid k-value crossing that we'll get to later. And that's some of the most important things that we touch base on. And then where most of I guess where most of engineers are actually coming in is actually there's probably a subset of people that does this job, but this equation of state model and the utilization of that model together with production data, fluid sampling data, different reservoir models, well testing, etc. That audience is huge and typically can involve everything from people doing reserves, marketing and sales to know what actual product are you producing versus oil, etc. to reservoir simulator folks and well testing folks and facility design. And that's really where we can create a lot of value add for the companies that we work for. And in very short, you take all the data that you have available in the field, not throw away anything as long as the data is measured. In all different formats from all the different laboratories, you try to create one basin-wide equation of state model, and that you can apply for all the wells in a particular field. And the question is then, okay, what is the criteria for when an equation of state model, or when one equation of state model cannot be is not sufficient for an entire field? The answer to that has to do with if there's very big differences in relative paraphenicity and aromaticity throughout the basin, either vertically or spatially, then you might need to have either separate equations of state or at least put some special treatment to the heavier components. But I think just to put things in perspective, from Curtis's 40 years or more from EOS model development and fluid characterization for reservoir fluids, all over the world, offshore, onshore, deep water, shallow water, Asia, South Africa probably, or Africa and South America and North America. How many times have you had to create multiple equations of state for a particular basin, Curtis?
Well, basin, field, yeah. I mean, where we've been tasked to try and given data from multiple, let's say, reservoirs or fault blocks or in a given field, maybe even neighboring sister fields, where we've been tasked to try to come up with a single equation of state that describes all of the samples in all of those reservoir units. On one hand, for sure, where we had to have more than one equation of state, and a couple of those happened in Saudi Arabia, where we did develop EOS models for all of their major fields, oil fields, and the differences there between one and the other equation of state was often in only the volume shift, and or the we split the heaviest component into a light and a heaviest component, and then the distribution of those two heaviest components varied from one reservoir unit to another layer or field, and that so it wasn't so the same component slate. Just so it's very seldom have we had to do it, and if it's required, then it's usually associated with the paraffin aromatic characterization differing from the one reservoir unit to the next. So different amounts of aromatics and different amounts of paraffinics, and so you either have to get a single equation of state, you have to have individual C7 plus fractions that are paraffinic and individual that are aromatic, and then you have a distribution that varies spatially between reservoir units. So it's the same EOS, but it's basically you're mapping the paraphinicity, aromaticity spatially, or you have to come up with different equations of state for different reservoir units. And I think it's less than 5 times in the probably hundreds of cases we've looked at. So it's a long answer, but very seldom. If you really need to do it, you can do it usually.
Very good. And from a high level, just the high level workflow overview. The first thing we would do is to go in and do the laboratory quality checks. Then we jump into C7 plus characterization, and there's a lot of time related to these two items. That's very important. And then the first thing we do is to create a initial equation of state model where we haven't done any extensive tuning. And as Bilal mentioned yesterday, and Curtis also mentioned, I think on Tuesday, that is actually a good QC in itself, especially if you have a lot of data, because the equation of state, if you inputted the data correctly, and if you haven't made any obvious mistakes, it should give okay initial predictions for most properties. After that we do the EOS model tuning, and once we've locked in the EOS model tuning, the last thing we do as an isolated exercise, because it won't affect the VLE properties, is or call it the K-value prediction tuning. Here in the simulation, and at least what we use is the LBC correlation with special developed in a special manner that we'll go through today, that ensures that you get monotonically increasing single carbon number viscosities. So when you get a denser and heavier fluid, you get a higher single carbon number or carbon number or component viscosity. Very good. The general overview, and this is kind of like there's just a summary slide of everything we went through on Tuesday. So there's different types of quality checks depending on what samples or depending on either all the samples or just the individual sample. So there are compositional checks that you can do on the sample itself, and that's related to the recombination exercise we also did the other day, comparing, for instance, the molar, the C7 plus distribution with the gamma. That's a good see. Every experiment that removes mass or volume from the PVT cell, which is for most practical purposes DLE separator experiments and CVD, you can do material balance checks. Also for the at least a few of the gas EOR experiments, you can do something similar. Then we have this is actually just one example, but you can use correlations or develop methodologies that are in certain realms deemed to be accurate to check, for instance, if the separator compositions or the separator samples that you collected are in equilibrium. We also have you can use the Z factor correlations to check if the Z factors are accurate or not. And when you get into more sophisticated experiments, which are more seldom, like ECM type of experiments where you can get high pressure K-value data, you can do material balance checks on that. And you can also even do that for the slim tube experiment, which we'll talk about tomorrow, but that measures multi-contact MMPE, minimum stability pressure. For all the samples, and that's what we say many times, having a lot of data is many times the best quality check there is. So to generate the trend plots for the most and key correlated properties are a very good way to identify outliers. Examples of that can be saturation pressure versus GOR, C1 and C7 plus content versus GOR, average molecular weight versus density. That's essentially the characterization factors and these plots, and then single phase densities and viscosities at the constant pressure and temperature. And here we have an example of oil densities at the saturation or at some pressure versus viscosities at the particular pressure. And here we see a nice trend between the two data, while we have some outliers here that we should not weigh during the regression. And here is another example where we, for instance, plotted bubble points versus C1 mole percent. You can probably also plot that versus GOR, because this is also correlated with GOR, and you can get a nice trend like this. Here we have CGR versus C7 plus mole fraction. Maybe this guy is an outlier and you need to be careful. And here we have an example of this important plot for C7 plus molecular weight versus specific gravity. And here we see the tuned Zerida correlation for those points, and the general trend, I guess, in general. A little bit rule of thumb, these two lists or these two next slides is just more for reference, just on what the type of uncertainties we typically operate with when it comes to the different measurements itself. Before going into each and every experiment, what is important to emphasize is that if you have uncertainty in the reported composition, and if your compositions are just measured totally wrong, you have a super bad baseline shift correction applied, or some issues with applying an internal standard or something along those lines, that will affect all the experiments. So that's probably the most important thing, is to have an accurate way of calculating and reporting compositions. And then for the different experiments, there also is an accuracy component related, or an uncertainty component related to each of the experiments. So CCE is something we know that measures the saturation pressure. And that's generally within plus minus 5 bar. So you can convert that to field for those of you who find that more relevant. But for gas condensates, for instance, it might be even larger uncertainties, because it can be very, very hard, even through a visual cell, to actually identify when that first bubble drops out of or the first drop of condensate drops out of the gas. The gas C factors are generally within 1 to 3%. I think 3% is typically also what we operate with when it comes to these C factor correlations, so that's good for QC purposes. Stock tank oil densities is within, if it's measured in the laboratory, typically within 1%. If you're talking about field measured APIs, there's so many things that can go wrong there, or that can lead to much higher uncertainties if you're working with a field measured API number. That can, for instance, have to do with how long the oil has been, exposed to atmospheric conditions and whatnot. So that's just something to be aware of. But in the lab, usually within 1%. These molecular weights, the stock tank oil molecular weight measured with this benzene freezing point depression method, is generally within 5%. But as Curtis mentioned the other day, it can actually be 5 to sometimes even 15% uncertainty on that, which is important to remember, as this is such an important number for the C7 plus characterization, especially this C7 plus molecular weight specific gravity number. Reservoir oil densities generally within 1 to 2%. Densities within 2%. The separated BOs 2%, and GORs, that's also a little bit depending on fluid system, obviously, and how much gas versus oil you actually have available to be measured in the laboratory. But between 5 to 10% is a good number. This is a similar list just for the different experiments that where I'll leave the DLE, CVD, and CC numbers more for reference, and the same goes for MM. We'll talk about more tomorrow. And I think a thing that's very important to emphasize is when it comes to oil viscosities. We talked about this. Gas viscosities are very, very seldom measured, almost never. While what is so it's typically calculated, but for oil there's very large uncertainties related to it, generally in the 10 to 20%, and it's also a very hard thing to measure, but at least compared to all the other parameters. But it's also a thing that's probably also the most hard thing to model. So that has it's kind of two sides of that story. Anything you'd like to add on this in particular, Curtis? This is important, I think, on viscosities.
Yeah, you're talking specifically about the
viscosity, the uncertainties in the oil viscosity measurements.
Yeah, I mean, it's definitely the most important data with highest experimental uncertainty, and sometimes variation that's real but difficult to model because of these varying paraphenicity aromaticities spatially. So if you get all of your oil viscosities within plus minus 20%, and the bulk of the oil viscosities you've measured within 5 to 10%, you should be very happy with that model, basically. So
a question that sometimes arises when we talk about viscosities is like, okay, if we only can measure viscosities on oils, like what do we actually do, or what's the recommendation for gas condensate reservoirs? And very briefly there, our general recommendation to keep things simple is just to take the condensate produced at surface, but essentially do an experiment because there you can take a lot of sample. That's not an issue. So you can take a sample of condensate at the surface, send that to the lab, and do the viscosity experiment just at the reservoir conditions with the separator or with the surface condensate from that well, instead of trying to recombine to find a condensate composition in the reservoir, make it drop out a little bit of liquid, and then isolate that liquid and do the experiment. That's very, very hard to do in practice, and probably the uncertainties are even greater when it's you'll be able to get so small quantities. While actually what's important for the tuning process is these heavier components that you anyway will find in the surface stock tank condensate. So I think that's an okay thing just to mention here for gas condensate fluid systems. Very good. So the general key takeaway on the QC part is that it guides the weighting factor applied to each PVT data point. And I think in general, the weighing, for instance, saturation pressures can be very important, because if you don't have your saturation pressures right, you actually don't have your K. That's kind of like a number that represents K values, and if you don't have that correct, that will compound onto the other different properties that you've measured, such as densities and relative volumes and all these things. So it's of some of the, at least personally, when I do the development, weighing that at least initially to get you on the right track helps a lot in the tuning process, because you'll then see a lot of the other data also start to fall in line. Very good. I don't know. From here, I'll leave you all with Bilal, and then we'll take a break in 18 minutes. Yeah, perfect.
I think we can go on this topic of C7 plus characterization, and there will be very comprehensive and interesting exercises on this, where we will actually go through the workflow that we will see in the presentation, practically in Excel. Yeah. Okay, so yeah, heptane plus characterization. I think we have went through the introduction part of it, like why, what is kind of an objective, because we know that these heavier fractions, if we look at here in this table, so if we go towards heavier and heavier fraction, this one single carbon number fraction C7, it has a lot of pure compounds. So like, for example, C7 has 9 pure compounds, C8 has approximately 18 pure compounds, and this is exponentially increasing as we go towards heavier fractions. And with this chemical separation techniques we have, or for example from gas chromatography, we cannot have enough resolution, at least for these heavier fraction now, with, for example, for C11 plus, that we can get the information on how many different compounds exist, for example, in C11 or C12 from the gas chromatography. So when we develop equation of state models, we have these components as single carbon numbers. That's the highest resolution we can have in the equation of state model using the gas chromatography data. And then we have to come up with the average properties of these heavier fractions, which again depend on how much relative amounts of the different types of pure compounds exist in this single carbon number fraction. So what is the relative amount of the different aromats compared to the paraffins and naphthenic compounds, for example. And that's something also we went through before. So if you want to do EOS calculation for any given pressure and temperature, the inputs that are required, number one is the composition. you need the sample composition for which you want to do equation of state model calculations. And then the second thing is the EOS model itself. And we know that the EOS model is actually comprised of two tables. One is the component properties, which in this presentation we will group as we will term it as theta I, which is a group of different component properties, the molecular weight. You need the TC, PC, and a centric factor, and then you have the volume shift. And then the second table is this binary interaction parameter table. So we need these two tables together with the composition to do any EOS calculations. Now these component properties that we are talking about, that's equation of state model table 1. We know that for these lighter fraction, that's 6 minus, we know the component properties exactly, because those are pure compounds, so we know what are the critical temperature, pressure, centric factor, and volume shifts for those compounds. But for heavier fractions, C7 plus or C11 plus, so this will be the case when we don't have any information on the single carbon number C7, C8, C9, and the isomer information, zinc, toluene, what compounds exist there. If we don't have information, then it's a C7 plus fraction. Otherwise, it's a C11 plus fraction. So for those compounds, we don't have the information on how these average component properties vary for those compounds, and that's kind of the objective of the C7 plus characterization, to come up with the average component properties for those heavier fractions in some kind of consistent way, and also come up with the mass and molar amounts. And from the PVT labs, we generally get those amounts for those heavier fractions, single carbon numbers until C30 plus or C36 plus. So in that case, the objective in this C7 plus characterization would be to quality check whether those amounts are reliably measured, and if there are any corrections to it, we will just do the corrections with some kind of model. So the one of the steps in the C7 plus characterization is to develop a field-wide molar distribution model. So that will be kind of the first step in the C7 plus characterization. And this field-wide molar distribution model, we went through this yesterday, and the objective of this would be to QC the lab reported amounts of these heavier fractions, because now you get those amounts in the lab reported data. You try to replace that bad quality, any bad quality data if it is needed there, and the gamma model should, if it's a well-tuned gamma distribution model to all the samples you have, it should reliably give you a good estimate of the heaviest fraction amount, which we know that it has the highest. So this one has the highest uncertainty in the measurement. So yeah. So in essence, you need the one of the key things or key tools in doing the proper C7 plus characterization is to have a field-wide gamma molar distribution model, and this molar distribution model gives reliable estimates of the component molecular weights, which we think are more representative or consistent for our fluid system. And it also gives us the amounts of the heavier fractions. So, for example, C7 plus fractions, which we can compare with the lab data and see if there are any lab data quality issues. So that's one requirement or one tool in the Heptane plus characterization. And then when we talk about the average component properties for these heavier fractions, we need in the equation of state model calculation, we need the TC and PC. And TC and PC are generally function of the boiling point and the specific gravity of each component. And these can be estimated with different correlations. We have 2 correlations. There are other bunch of correlations that are given in chapter 5 of the monograph. So this for the 2 correlation that's in PhasCom uses the boiling point and the specific gravity of each component. So you require you would like to know what are the boiling points of each fraction, and you would like to know what are the specific gravities of each fraction. And in the EOS table, we need TC/PC. We also need volume shifts, and volume shifts are a function of specific gravity. That's something I briefly discussed before, that the way volume shifts are calculated in most PVT packages now is that you provide the specific gravities of each component, and then it calculates this volume shift factor or the correction factor to the density that exactly gives the user input density for a given component with an equation of state model. So it just finds with an equation of state model, the PVT package just finds the volume translation parameter needed to get the right specific gravity given by the user in the EOS model table. So that's function of your specific gravity. And then the eccentric factor is generally a function of TC/PC and the normal boiling point, which we already have here. And that can be calculated, for example, from Edmistor correlation, and PhasCom have some special method. And now actually the software that Kappa is developing, which is now Carbon. So that software also has the same feature as PhasCom. And the binary interaction parameter. So as I mentioned before, that this is from this we generally get the first order estimate from this Jew correlation, and where we saw that the binary interaction parameters, they are a function of the critical volumes, and these critical volumes, or you can say the Z factor, the critical Z factors. So and these critical volumes we can again estimate, because that's just the critical property of each component. It can be estimated from some kind of correlation like 2 correlation or Lie correlation. That's also in chapter 5, knowing the boiling point and the specific gravity of each component. That's why if you look at this table, equation of state model table here, you see that we have that ZC and the critical Z factor values here. And these Z factor values, they are not used in the equation of state model calculation, because EOS models, we know that it requires molecular weight, TC/PC, eccentric factor, and volume shifts only, and then A and B. So this ZC value is just there so that we can get the of the binary interaction parameters. And these ZC values may be different than the ZC values we are here, which is only meant for the viscosity calculation, ZC vis. And that's something we will see when we will talk about the LBC correlation. So in summary, what we went through, what we have went through here. So like to do the C7 plus characterization, the different tools that we need. Number 1 is this field-wide gamma distribution model. This is gonna give you the amounts of the different fractions for these heavier components, and also it is gonna give you some estimate of the component molecular weights. Knowing the component molecular weights, we can estimate the component gravities. That's our second tool that will be used to develop or to do the C7 plus characterization. So to develop the field-wide molecular weight specific gravity correlation, or you can say the characterization factor, Watson characterization factor, or this FC, that's the Sereda factor, or you can there are different correlations available. So we will have to just pick one correlation and try to tune that correlation to any measured data that we have to get the estimates of individual component-specific gravities, knowing the molecular weights, for example, from this molar distribution model. And then the third thing is to come up with the boiling points of individual fractions, again, as a function of molecular weight. So we will see how we can develop a field-wide boiling point molecular weight correlation, or we can use some other correlations that are available in the literature, for example, two correlation. So these are the three main tools that we are going to develop in the C7 plus characterization to develop the equation of state model. And we will go through some of the literature here in the PowerPoint, and then try to do the exercise in the Excel file. During the rest of the day, we will go through the this presentation, and we'll talk about the EOS model development workflow. And as we have mentioned before in the previous slide, we have these three main tools for the C7 plus characterization, which is the essential ingredient when we develop the EOS models. Field-wide molar distribution model, that's usually the gamma distribution model we use. And then we have the field-wide molecular weight specific gravity correlation and the boiling point molecular weight correlation. So first we will go through the details of the gamma distribution model, how we develop the models for multiple samples. We went through this also yesterday. So just a short recap on what we went through before. Gamma model, again, used to describe the molecular weights of individual fractions and mass in moles. And it has three parameters: shape factor, lower bound, and the average molecular weight, which describes the continuous distribution of mole fraction versus molecular weight. And then we have, in addition, these lower molecular weight boundaries that are required to discretize the continuous function to get the estimates of molecular weights and the amounts of individual fractions that we are interested in. And now in the modern PVT reports, we usually have the extended DC data. So in that case, we use this molar distribution model and tune the parameters to the available lab data. And when we do that, we usually try to come up with a fixed set of alpha, eta, and the lower molecular weight boundaries for all samples. So there is a constant value of shape factor and the lower bound and the individual component lower molecular weights that are applied for all the samples. And then we have, for each sample, we have different C7 plus or C10 plus molecular weight, depending on where the distribution starts. And for that purpose, we use the GC data of the surface oil samples. And in general, what we expect from the tune model, that it should give the reasonable match of good quality lab reported GC data, some mass amounts of these heavier fractions. And if you have good quality measured average molecular weight of the stabilized oil, then those should also be reasonable with the tune gamma distribution model. And this tune gamma distribution model also gives us a consistent set of individual component molecular weights together with the amounts. So what is kind of workflow for developing the gamma distribution model? So what we do, we take all the samples. So here we can see, like, for example, 4 samples. So this is maybe an oil sample, maybe a volatile oil. This is maybe a black oil, near critical fluid, a gas condensate, for example. And then for each of these samples, we have the lab reported mass fractions of individual components. And here J represents the number of samples. And then we have, on the other hand, we have a gamma distribution model where we have where we need an alpha, the shift factor, the lower bound, the lower molecular weight of each component, and then there is a sample specific average molecular weight. So these are the parameters that go into the model, and the model predicts the weight fractions of each component for the different samples, and then we just try to minimize the difference between the lab reported mass fractions and the model mass fraction, and the regression variables are these. So these one shift factor, one eta, and for each component there is one lower molecular weight, and then for each sample there is an average molecular weight. And when we do this minimization in the regression problem, we get this field-wide gamma distribution model. So this is again, we saw this figure also yesterday. That's what we expect from the gamma distribution model to give us reasonable amounts, a reasonable match of all the samples.
Just a question.
That's all about the gamma distribution model. Yes, Gulnar?
Yeah, if you go back to the previous slide, you showed all the different fluid types.
Yeah.
Does it matter that the lab report, for example, reports one is until C20 plus, another C36 plus, the third one is C10 plus? What do we do then?
Yeah, very good question actually, and it's a very practical question. So what Gulnar is asking that if we have for different samples the lab reported heaviest fraction is different for the different samples, in that case what we are gonna do. So let's say if we have this sample may have, for example, lab reported C36 plus, this one may have a C30 plus, and this may have for example C20 plus. So what we will do in that case, for example, we will again use all the samples in the model tuning, but now we know that for example when we will be matching the lab reported amounts, in this case we will be matching the lab reported amounts for all the fractions until C19 or C20. Here it will be until C30 plus, and here it will be C36 plus. And still we will have a common shape factor and the lower bound and the lower molecular weights of each sample. But now, since we have only one sample with, for example, where the amounts are greater than C30, so the amounts are greater than C30. So we know that, for example, in this case where we have only one sample where the amounts are greater than C30, so the confidence on your molar distribution model for these very heavy fractions will not be too much. But like, for example, we have 3 samples at least where we have the amounts less than, for example, C20 carbon number. So now we know we will be more confident in the model calculation for all the carbon numbers until C20, for example. And is that what Gulnar, is it clear or?
Yeah. So basically what we're saying, we can until C19 we can be sure on the number 2, right? Until C29 we can be sure using the gamma model distribution, and here we can be sure until C35, right? And the rest, is that what you say?
The gamma distribution model also gives you the amount of the heaviest fraction. So you also get this C36 plus, C30 plus, and C20 plus. But yeah, but what I'm saying here, that since we have, like here in this scenario, we are assuming we have only 3 samples, for example. and the 3 samples have different heaviest fraction. So the last sample, it has the heaviest fraction until C36 plus, and the amounts for carbon numbers heavier than C30, they are only present in one sample. So when we will be tuning the gamma distribution model using all the samples, we will be more confident in the gamma model prediction for all the carbon numbers less than C20, because they are present in this sample, in this sample, and in this sample with the same gamma distribution model. So the gamma distribution model will be more robust for these carbon numbers. But then for between C20 and C30, we have only this sample and this sample. So the confidence will be a bit less, and then for greater than C30, it will be even lesser. But if you have more samples, like if you have 10 samples or 15 samples with this kind of variation in the lab reported heaviest fraction, the gamma distribution model will be more robust.
Okay. Yeah, thanks.
Okay, so the next thing on the list for the C7 plus characterization is to develop the correlation between the normal boiling point and the molecular weight. And there are different correlations available in the literature, but what we internally try to do is to develop a field-specific molecular weight boiling point correlation. And to do that, what we generally do is we know that these lower molecular weight boundaries that we get from the gamma distribution model as a regression variable, which ensures that you have a good fit of the GC data. These represent the boundaries of your single carbon number. So these are the boundaries of GC fractions in terms of the molecular weight. And then in terms of the boiling point, we can also have the boundaries of each single carbon number fraction. And what information we have for single carbon number fraction, that for example, if we have a C7 fraction, then we know that the C7 fraction, this single carbon number fraction, it is comprised of all the compounds that boil off between the normal boiling point of NC6 to, for example, PV of NC7. So the lower boiling point for single carbon number fraction, that can be the boiling point of normal C6. Similarly, if you have C8 single carbon number, then this would be the lower boiling point. That's kind of the boundaries of the single carbon number fractions in terms of the boiling point. Is there somebody who's trying to say something? Where is the sound?
Eirik, you have a comment?
No, sorry, just my microphone was.
No problem.
Yeah, no worries.
Yeah. And then when we have these lower molecular weight boundaries from the gamma distribution model, and this TBL, the lower boiling points, these are just the normal paraffin boiling points, which are known for all the normal paraffin compounds heavier than C7 plus. We can correlate them shown on the next slide, and then since we have already developed the gamma distribution model, we know what are the estimates of average molecular weight of each carbon number here. So from that correlation, we can actually calculate the average boiling point corresponding to the average molecular weight. So this is the kind of correlation we can develop, and we will see in the exercise that we can correlate the lower normal boiling point temperature and the lower molecular weight. This is all the data that you have, and then this is just a trend line fit to the data. and then this could be your TBM correlation. So now knowing this X, which will be the average molecular weight of each carbon number coming from the, for example, the gamma distribution model, we can estimate the average normal boiling point. So that was the second thing on the list. And the third thing, that's the third thing on the list, the tool that we need for the C7 plus characterization is the field-wide molecular weight specific gravity relationship. And we already have gone through this, that the average properties, TC, center factor, those properties depend on the relative aromaticity, paraffinicity of each compound, which may be different from one field to another. And one way to estimate that average relative aromaticity, paraffinicity in the fluid is to establish this molecular weight specific gravity relationship. In general, you can say that the gravity is related to the gravity of each compound is related to the molecular weight of each compound with some kind of characterization factor. So that's the C here is a general characterization factor, which could be a Watson characterization factor or a Sureda characterization factor or Jacobi aromaticity factor. There are different correlations available in the literature which you can use and fit any available data, measured data that you have. And the data that we usually use to tune that correlation, so the number one is the C7 plus average molecular weight density available. That's the most common data that is usually available for this kind of tuning of the correlation. And always again make sure that when you use the C7 plus data, you try to use the measured data like we back calculated yesterday during the exercise. So we will use that instead of the calculated data. But again, the best piece of data that you can use actually for this kind of relationship is this single carbon number distillation data with measured molecular weight and specific gravity of each fraction. And that's the most recommended data for this kind of analysis. And to have that data, like we usually recommend that at least for one field, you should have that data. And it's not very expensive to get that data. For example, it may cost you about $10,000, which is relatively very cheap compared to the other PVT experiments that you do in the PVT lab. Yeah. And once we tune our correlation and we find out, okay, what is the best characterization factor for our field, then you actually establish this relationship between gravity and molecular weight. And with that relationship, knowing the average molecular weight that may come from, for example, gamma distribution model, you can estimate the gravity of each component. Yeah. Which may be representative of your field. So this is an example of how to utilize, for example, TBP data. And there was one question yesterday, like how you integrate the GC data and the TBP data together. So this is one example. Like if you have TBP data measured on single carbon numbers, so this is one example how, for example, the gamma distribution model, which is tuned to your GC data and the TBP data, it should be able to give you good predictions of your molecular weight. So these black numbers here, these represent the molecular weight, component molecular weights coming from the gamma distribution model, and here you have the component molecular weights from this ASTM distillation. And that's just the diagonal line, and this should give you very good estimates of the gamma distribution should give you good estimates of those component molecular weights, and then you have the Sureda correlation. So this is the Sureda correlation here shown, which is which can be fit to your TBP data, the measured specific gravities. And just to highlight the Sureda correlation, if you will find out, if you will see in chapter 5 in the monograph, the Sureda correlation is this number here. So you have a CF here, average molecular weight minus 66, and then you have in the exponent you have 0.13. So this guy here, that's the CF, that's the Sureda factor, and then this is in the default correlation, that's 0.2855. This is 66, and this is 0.13. And generally, we recommend only to change the characterization factor only and keep all other values default to the default value. If you have only a very limited data, like for example, in this case, when we will develop the EOS model samples, so we have only 2 points on this curve. One is the C7 plus molecular weight gravity from the gas condensate, and the other from the black oil sample. But if you have more samples, or if you have this kind of data, the TBP data, and you have the data covering a very wide range of molecular weight and specific gravity, then you can you can use or change the other default parameters in any correlation for and just try to match your lab measured data and come up with your field specific molecular weight specific gravity correlation. And what is kind of a litmus test of whether your specific gravity molecular weight relationship is well tuned to your lab data? So the litmus test is that we know that the volume shifts for each component in the equation of state model, they are mainly function of your gravity, the specific gravity. So because the volume shifts are calculated to match the given component specific gravity, so it means that if you have done this kind of characterization, and if you use that equation of state model with these volume shifts, it should be able to give you very accurate surface oil densities. So the densities, the surface oil density should be within 1 to 2%. So that's kind of one litmus test of our C7 plus characterization, that you have done everything right, and that is to check the surface oil density prediction with your initial EOS model that is based on the C7 plus characterization workflow we are going through now.
Just a question on the Sureda correlation. So basically, for the given field, this CF should be constant?
Yeah. So for a given field, yeah.
Okay.
Yeah. Yeah, that's right. So for a given field, it is a if you're developing a common equation of state model, and we believe that the common equation of state model can be developed for all the samples in the given field, then there is a constant value of CF for all the samples. And that constant value of CF leading to some kind of specific gravity molecular weight relationship should be able to give you very accurate surface oil densities for all the samples. Okay. Do you have any more question, Guldar?
No, thank you.
Yeah, so characterization factor, this is exactly what Gulnar was asking, that the characterization factor, it can vary from one basin to another, one field to another, maybe from one reservoir to another. And common characterization factor if you can find one common characterization factor for all the samples, that is usually a very strong indicator that you can successfully develop a common EOS model, because a common characterization factor means that you have accounted for this changing relative aromaticity, paraffinicity in the different samples with a unique and common specific gravity molecular weight relationship. Okay, so yeah, so that's just the key takeaway, and that's the objective of the C7 plus characterization, that the properties of C6 minus is all known. C7 plus is less known and more complicated, and therefore it requires this special treatment that we call it C7 plus characterization to come up with the average representative properties for the field we are working on. So we can go through the exercise, and I can show the exercise here. I can just open the solution and just explain what is done, and it should be easy to follow. And I guess you can go through the solution solved version at your own pace at home and come up with any questions if you have. But before we jump to the exercise, are there any questions or comments related to the topic we just went through? Because this is a very fundamental thing in developing a good initial EOS model, and we believe that if you develop a good initial EOS model with and spend a good chunk of your time on this C7 plus characterization, then you do not need a lot of complicated EOS tuning. Usually, if you have very less data, if you have a very small amount of data for EOS model development. Okay. I don't know why is this open. Okay, so I think we can start the exercise from here. So the first thing what we are gonna do in the C7 plus characterization. So what we went through in the PowerPoint, we need three things: gamma distribution model, a specific gravity molecular weight relationship, and a correlation between the boiling point and the molecular weight. So first, we can see how we can develop the molecular weight specific gravity relationship for the fluid system we have in this course. So these are the two samples, the black oil samples, the black oil and the near critical gas condensate, and we have the C7 plus specific gravity and the molecular weight. So this is the C7 plus specific gravity, and this is the C7 plus molecular weight and C7 plus specific gravity, and these are the numbers that we calculated yesterday we back calculated yesterday from the measured average molecular weight and specific gravity. And this is just the weight factors given to each data point, and then here this is specific gravity calculated from this is just use the default values first. So this is the specific gravity calculated using the average molecular weight of C7 plus and this AREDA correlation here. And here we are just using, so these are the default values of all the parameters. The CF the default value is 0.29, and then and this 0.29, you will see that if I go here, for example, you see that what I have plotted here, this blue line here, the dashed blue line, that's Kac-Perza-Body. Specific gravity molecular weight data that labs generally use. And then this black line, the solid black line, that's the Soreda correlation, and it's not tuned to our data points, the 2 data points we have here. And you see that the default Soreda correlation with the CF of 0.29, it falls very closely on top of the Kac-Perza-Body. So what we see that our fluid system is slightly different than the relative aromaticity paraffinicity Kac-Perza-Body have, and that's what we also saw when we calculated the Watson characterization factor the first day, that the Watson characterization factor for this fluid system was slightly higher than 12, and then for Kac-Perza-Body it's about 11.9 or something. So yeah, so our fluid system is slightly more paraffinic than the Kac-Perza-Body. So we will try to tune the Soreda correlation, and again, since we have very limited data, so we will just keep all these parameters here to the default values, which are here, and then just change this factor, the CF factor, to match this data, these 2 data points, or try to minimize this sum of squares. If we just go and then solver, and I think everything should be, we are trying to minimize this number here by changing this Soreda factor, and then so it calculated a CF that's less than the default CF, and these numbers here these are just the arbitrary molecular weights to just plot the data. So 80, 100, 120, and we have calculated the specific gravities using the tuned Soreda correlation. So if you go here on the plot, so now you see that this black curve is now falling closely to the lab data, and this correlation should be able to give you reasonable results on the liquid phase densities or the surface oil densities in our equation of state model. Okay, so that was one thing that we had to do. Any questions here, or there was something that that was not clear? Okay, so the next thing on the list was more complicated thing, that was the gamma distribution model, and yeah, so the gamma distribution model, it is part of PhaseCom. So in PhaseCom you can use the distribution model, gamma distribution model, and do the tuning of the GC data automatically, doing the regressions in PhaseCom. Somebody commented yesterday that PVTP also has the gamma distribution model, but I have also some experience working with PVTP when I was not working at Whitson, working in Pakistan, and the gamma distribution model that PVTP has, there you can define the alpha and this beta parameter in the gamma distribution model, and then it gives you the distribution of the heavier fraction. But again, there if you want to put some values of alpha and beta, then you would like to know what alpha and beta your fluid system have. So in that case, you will need to match your lab data with the motor distribution model. And in that case, you can use, for example, this Excel file to come up with the motor distribution model parameters. Okay, so when in this exercise, in this study, or in this exercise samples, we have the black coil sample and the near critical gas condensate, and it was mentioned in the PowerPoint that when we develop the gamma distribution model and use the extended DC data, we should try to use the surface oil samples. So here we have the flashed oil and separator oil. And the reason why you should prefer the surface oil samples, so number one is that the data, like these are the samples where you have the measured data. Like they are measured directly in the PVT lab. And the second is that they have the surface oil samples have the highest resolution of the C7 plus amounts. So these amounts, because we know that, for example, flash oils, they have about more than 90% moles. Mole fraction is actually the C7 plus in usually in the flash oil. So we should be using the flashed oil, and you can also use the separator oil, which again has some higher resolution compared to the recombined samples or bottom hole samples. And we should be using the mass amounts because we know that those are measured in the lab. So that's why here we are using for black oil the flash oil sample, and here we are using the separator oil sample for the near critical gas condensate. We could have used also the flash oil from the separator oil for this near critical gas condensate. Yes, Gerardo?
Yeah, sorry. So just for me to be clear, so you can have downhole samples that you flash. Let's take a DST string, right? So I can take downhole samples I can flash. I can also take samples if I'm in single phase at the wellhead. And I can also take samples at the outlet of the separator. And from all of those, I can have a flash oil.
Yeah.
So which one, from your view, is preferred, and what's the reason behind?
Yeah, so what we are trying to convey here, that all of the flash oil, whether it's a flash from the bottom hole sample, it's a flash from the separator oil sample, or a flash from the wellhead sample, all of them should be used simultaneously in the gamma distribution model, because the measurement uncertainties in the lab data, those are not connected to the origin of the sample, right? So if it's a bottom hole sample, the laboratory DC measurement uncertainties doesn't know whether it's a flash from the bottom hole sample, or it's a flash from the wellhead sample, or the separator oil sample. So the flashed oil is a flashed oil at ambient condition, and in a field, the same distribution model should be able to match the good quality lab measured DC amounts for any sample.
So what you're saying is we should look at all of them to ensure consistency, but none of them are better than the other.
Yeah.
Okay.
Correct. Yeah.
Okay.
Just a question, can you please elaborate? So you're taking a critical sample. What's the separator oil? It's a bit unclear.
Yeah. Yeah, so I guess we can look at the PVT report. I think we should. If I open the gas condensate, PVT report. So we know that we have two PVT reports, and one is the black oil PVT report, and on the black oil PVT report it says it's a sample type, it's an open hole formation testing, so it's a bottom hole or MDT type sample. And then we have gas.
Yeah, the black oil is clear. We're taking the flashed oil composition, but the gas condensate. Oh my God.
So in the gas condensate PVT report, it says the sample type is separator samples. So it's a separator recombined sample. So we should have a separator oil and a separator gas sample here. So you see that we have a separator oil compositional data, and from separator oil, and the separator oil has a flashed oil and a flash gas. So the separator oil that we see in the Excel file, that's this separator oil, which is reported in the gas condensate report. And what I was mentioning there, and that also something Gerardo was trying to ask, that I could have also used the flashed oil reported together with the separator oil here. So I could have used either this, or I can also use this separator oil. Is that clear, Gulnar? Or
Okay, so for oil case, you're using the flashed oil. For gas case, you're using the recombined
separator
oil separator oil. Okay, yep.
Yeah.
But that's just because that's the data we have available in this report, right? So if we had an oil well that was recombined that with separated samples, we use the separated samples for that well. So it's just based on what data we have available for the different wells.
Yeah. But you can also use, for example, from the gas condensate report, we have a separator oil sample, but you can also use the flashed oil, which we know is directly measured and it's not a mathematically recombined sample. Because the separator oil sample, here you may have this mass fractions here. We know that it's not measured directly. It may have more uncertainty. It may have additional uncertainty due to, for example, recombination GOR. That's exactly right. But the uncertainty in the recombination GOR will not affect the distribution of the C7 plus fraction, the relative amounts, and that's the objective of the gamma distribution model, to match the relative amounts of the C7 plus, or the distribution of the C7 plus fraction.
Yes, to summarize, it's just a bit confusing. So we can use any oil composition, in this case, the flash oil of the separator oil. We should expect the same results.
Yeah.
Doesn't matter any other. It's not that we need to double check all of them. Well, if you want to do it to check consistency.
No, yeah.
Okay.
That's the point.
I think, Bilal, I think at the end of the day, any and all flashed oils, from a reservoir gas, a reservoir oil, or a separator oil, those are the three sources of your flashed oils. Any flashed oil and all flashed oils can be gamma model, fit to the gamma model, and should be. Any other mixture compositions, just stay away from them, because the information in the heavy ends from like a separator oil itself, or the reservoir oil, or the reservoir gas condensate, the information about the distribution of the heavies comes from a flashed oil. So it's better just to do the gamma modeling on only flashed oils, basically.
Yeah.
I think that's the simplest way to make it.
Yeah, and that's what we do internally. But the reason why we are using separator oil for gas condensate instead of the flashed oil in this exercise is just because to make the life simple for you and for us also, like during the exercise. Because if in the exercise, if we do the gamma distribution modeling on flashed oil, then we will have to do the recombination of this flashed oil and flash gas to get the separator oil, and then use the calculated separator oil and the separator gas to get the total sample composition. We will have to do the two
It's just more for convenience in the classroom environment. But practically all of the information about the heavy ends distribution that would be natural to fit to a gamma distribution model will always come from flashed oils, basically. Even though you could use separator oils if you wanted to.
Yeah. And sometimes that they don't provide you the flashed oil composition. So for example, like, there was one study we were doing Eagleford, the basin-wide study. There were about 60 samples, and from the same lab, and all the samples were separator recombined samples, and none of the separator oils had a flashed oil reported in the PVT report. So in that case, we were just forced to use the separator oil samples to develop the gamma distribution model. Okay, so but this is again it's a good exercise for you to do at home, or if you have time. Just replace the separator oil composition here, and then just replace it with the flash oil that's reported in the PVT report, and just do the same exercise and see if you get the same gamma model parameters or not, or like very similar gamma model parameters. Okay, so these are the lab reported data we have. And this sheet that Curtis was mentioning yesterday, that this is programmed for the gamma distribution model. It looks complicated, but I will try my best to make it easy for you. So on the left, we have the shape factor, the bound. This is again the alpha, and usually we try to keep it fixed for all samples. The lower bound, this is again, we try to keep it for same for all the samples. The gamma C7 fraction. Then this is total RMS. We will come back to that. What is it? And then for these are just the carbon numbers we have. So we are going until the C26 plus fraction. And then these are the lower molecular weight bounds. The lower molecular weight bounds for the different components. And here the lower molecular weight bounds are calculated with this simple linear relationship where we have the slope m and an intercept c, and these are the two numbers that we will try to change, and we will try to develop or match the lab reported data. And this is just a very simple way of regressing on the lower molecular weight boundaries. But like when we do it internally in PhaseCom, we try to change individual numbers because the PhaseCom regression engine is very fast and very reliable. So we try to change individual numbers to better match the laboratory data. But these numbers here, these are just from this linear relationship here. And then this column here, which is upper molecular weight bound, these are the same numbers on the left. So the upper molecular weight bound is the same as the lower molecular weight bounds for example, for C7 fraction, the lower molecular weight bound is the same as the upper molecular weight bound for C6. So 102.98 is here, 114 is here. And the reason why we have this column here, because in Excel, when you use this gamma function, the probability function, it uses the upper bound and not the lower bound. So that's why we have to have this column. And then this number for the last fraction, this is just an arbitrary, very high number, just to ask the model to integrate to the infinity. So this is just an arbitrary high number to get the amount of the heaviest fraction by integrating the model from this boundary to some very high number which represents the infinity limit. Okay, and then these are so this one table here, this is for one sample. This one table for one sample, and then this is for that sample too, actually. That's another sample, the near critical gas condensate. And then we have average molecular weight. So that's the C7 plus molecular weight. This is from the lab data. And we can start from the lab data actually. So 261. The initial value is the same as we got from this from the lab value, the back calculated value from the average measured molecular weight, and here it's 189. And then these numbers here, these are actually programmed from these equations that are in the monograph. So equation 5.22, 5.20, 5.19, 5.17. Here, these are the normalized mass fractions for each compound, for each fraction, C7, C8, C9. And this is from the lab data. So if you look at this formula here, so what this formula is doing, it is taking the amount of the 7 from the lab data, which is connected to this previous sheet. So for example, for the black oil, what it is doing for the C7, it is just calculating the normalized amount. So this number, this amount of C7 divided by the sum of C7 plus, which is fixed now. So if I just, so this is 0.0286 and 0.0287, yeah. So this is how these normalized mass fractions are calculated from the lab. And these are the numbers coming from the distribution model. And then we have assigned the weight factors to each data. And generally, we know that the last fraction has the highest uncertainty. We generally try to avoid giving any weight to that. So that's given a 0 weight factor, and that's something we will be just predicting with the gamma distribution model tuned to all the lighter fractions. So that's the same. So this is for one sample, and the same goes for this other sample here. Okay, and just to make this exercise more interesting, what we can start with is actually an exponential model, which PVT sim uses, right? So if we let's say, for example, a shift factor of 1, we know that that's the exponential model. And also the bound, we know that the other limitation of the exponential model is that the difference between the difference between each molecular weight, the 2 consecutive molecular weight has to be 14, and it means that the lower molecular weight boundaries has to be exactly in the middle of the 2 component molecular weight. So this has to be, for example, we can start from 93, for example, and then here it should be, that should be 14, and then this should be 93. So this should, so now yeah, so you see that the molecular weights, that's 100, 114. So the difference between the 2 consecutive molecular weight is 14, which is the characteristic of the exponential model. And the shift factor is 1, that's alpha. We can also, but here we know that now, for example, for C7, the average molecular weight is the normal haptane molecular weight. This molecular weight is the normal octane molecular weight, and we can shift those numbers by some constant value. So, for example, which is the h, which was the h factor that we saw in the exponential model. So if we want to shift it by, for example, 4 units, so let's say 89, and then we have to change it for 89. Yeah, so now again, so now these are the molecular weights. These are the molecular weights very similar to what you get in PVT sim, for example, with an exponential model and with an h of -4. So because the average molecular weight is 14I plus h, and so for normal heptane, for C7 carbon number, you will get about 96. 110 for C8, 124 for C9. So if you look at only the predictions of this distribution model for the two samples we have, this is sample 1. Okay, and you see how this distribution model looks like compared to the lab data, and then this is the other sample we have. Okay, and now yeah, so now what we are going to do is we will try to tune this molar distribution model to this lab reported GC data. And to do that, we know that this shape factor and this lower bound, it has to be constant for the two samples. So this is one variable for the regression. This is the other variable for the regression. And then we have the sample specific average molecular weight. So this is another variable for the regression, and this is another. So we have these 4 variables in the regression. And then we have these 2 additional variables to change the lower molecular weight boundaries with some limited variables. And we will try to minimize this, which is the total sum of squares. So this is the RMS of the fit to the lab reported GC data for one sample, and this is for the other sample, and this is just the total sum of squares. So we will just try to solve using the solver, and so it is already set up minimization with all these variables that I have mentioned. We'll just try to push solve and see if it works or not. It's done. Okay, so it has converged. So that's a good sign. So what the model is giving us, we can look at the results. How do they look? You see how good is the match to the lab data for this black hole sample, and then we have this gas condensate sample where we have some mismatch here for the heavy fractions and some mismatch to this heaviest fraction, and this is representing that there is some if you believe that the model is exactly right, and usually the confidence in the model increases as you have more and more samples, and if you see this kind of behavior, then and you trust your model, then you say that okay, we have some uncertainty in the lab reported mass amount which may be affected, for example, due to baseline shift or internal standard. But if you look at the gamma model parameters, so you see that now the shape factor is 0.78, which is between what we which is similar to what we generally expect, about between 0.55 to 1 or slightly higher than 1, and the bound is about 96. These numbers are also changed, and then we have the average molecular weight 258 for the oil sample versus the lab reported value of 261. And then for this gas condensate sample, we have 181 against 189. And then we have the gamma model also gives us the average molecular weight of each fraction. So 99, 909, 121. And you also see on the gas condensate sample, and you see that the 2 values are very similar, because we have the common distribution model, and the only thing that's different from this sample and this gas condensate sample is the average molecular weight. Other than that, everything is same with respect to the gamma distribution model, and this average molecular weight mainly affects the molecular weight of the heaviest fraction. So you see this guy here, it's 509 for the oil sample, and it is 422 for the gas condensate sample. And that's one one thing about the common equation of state model, that we have one single heaviest fraction, and we know that that single heaviest fraction, the properties of that single heaviest fraction may be different, for example, for a black oil versus a gas condensate. And that's why that heaviest fraction is the most unknown in the common equation of state model. And when we tune the EOS model, that is usually the first component where we try to change the component properties to match the lab reported data, because that's the most unknown component. And also we know that it is somewhat different from one sample to another. Curtis, do you have any comments here?
No, I think you know, it's more driven by if there's any questions amongst the participants. I mean, it's unfamiliar, the whole gamma modeling. So I think we have to just play off of the questions that might be there from the discussion. So
A question regarding the in the solver, did you give any range that it has to go in? In the shape and the bound. When you run the solver, that it knows which range it should start. Okay.
Yeah, so you see, I have added some constraints, and one reason why I had to have a lot of constraints here is because the solver here, like if you have a lot of variables, then it doesn't necessarily converge to the right solution. So it
will pick up unlogical numbers, right?
And also sometimes it just crashes without minimizing the sum of squares. So that's one problem with the solver. And like for us internally, we use FaceCom, and we know that it has a very good regression engine, and it almost never crashes during the regression. But when you are using Excel, then that's just something you have to live with. Or maybe you can actually program this in Python with your internal or with some solver that you like better, and just do this with your programming skills.
Yeah. There is a package called SciPy that has quite a bit of solvers.
SciPy?
Yeah.
So we have Marcus here, the programming expert. He has worked a lot with Python. So yeah, so Python has this package which Marcus is mentioning. So you can have a look. And there is.
I think. Oh yeah, you were going to talk about this LinkedIn.
Yeah, but you can mention Curtis.
Well, I don't remember the person's name or anything, but there was an engineer who posted Python code to do this same kind of thing. I don't think any of us have taken it and tested it, but it's on LinkedIn. I don't know how you search for it, but there is code out there to do specifically this, I believe.
He has a GitHub repository.
I will have to sign, but the name of the guy is Dimitri. Maybe I can write it here.
I can send a link to the article.
Okay, yeah. So Matthias will send a link to the article. That's very good.
Do we have this? Do we have this Excel in our under the exercise folder?
If this Excel sheet that you're using, it's part of the exercise material.
Yeah. It's in the material.
Yeah. Okay. Good. Thank you.
Yeah. So that's an exercise on C7 plus characterization. You can find it with this name in the exercise folder. Okay. Any more questions? Hans, yes?
Just something to think about. Since I'm a lab man,
yeah,
and do you always believe on the gamma distribution that this is the correct? We work in the lab. Is it sometimes could it be that there is some deviation since we are we get some of the gamma distribution since we are analyzing the real samples, that it could be something with the samples? Do you always believe on the gamma distribution and say that if this lab results deviate from this gamma distribution, this is something wrong with the lab data?
Yeah, that's again.
I'm only a lab man, so I'm just wondering that. Okay, mathematics is you only got a smooth curve when you do the maths.
Yeah.
But it could be something.
I think maybe the short answer to that, Bilal, would be that when you only have one sample,
yeah,
we would never make such an argument. It would have to be falling so far off the trend. In other words, let's say it fits exactly or very well from C7 to C20, and then it just like falls off completely thereafter. Then we would probably raise the red flag and talk to the lab and so forth. But if it's just the type of deviations we're seeing here, the basis for us often going with the gamma model as a kind of like what should be consistent with the lab data is we have 20, 50, 100 samples. And we see that 80, 90% of those are just fit so well by the gamma model. Yeah. It's not probably logical that these other 10 or 20%, or it might be 5%, don't. Yeah. But so no, it's not a priori that it's going to be right or more correct than the lab data, no. But if you have the vast majority of samples are very well predicted with a consistent gamma model, and why are those 7% of the samples not being predicted?
Okay. I agree with that. I think so. Thanks. Well, yeah.
Can you make a comment on the smoothness of the curve, maybe? Because when you're changing the lower molecular weight.
Yeah. Yeah, but I can just make a comment on that now. So yeah, so where's the PowerPoint? Yeah. So there is just one quick thing that I can mention here, and that's what Marcus is saying, that if you look at, for example, this gamma distribution model, okay, and this is with the real lab data, what you will find out that the distribution is not smooth. So like, for example, it is following the trend of the measured data. So like, for example, when it was going like this, and then it was going like this, and then it jumps up and then goes down like this, and then goes like this. So it is following what we call as the character of the component, because this character of component could be real, even though it falls, for example, maybe the data falls on an exponential distribution, but these components may look like, for example, this on a log scale. So so what we try with the gamma distribution model, that we try to change these lower molecular weight boundaries to better match these character of the compounds, which we think should be real and should be consistent with all the samples that we find in a given field. Like, for example, if we see here, what we see is that the distribution is smooth, because here the lab data is also smooth, and we know that this data is kind of synthetic here. But here, when we are trying the gamma distribution modeling, we are trying to change the lower molecular weight boundaries with very limited variables, these two numbers. And again, because of the limitations of this Excel solver, but in the studies that we do, and if we have a lot of samples, we generally try changing the lower molecular weight boundaries individually for each compound to better match that character of the component. And that doesn't give you a smooth function on the gamma distribution model. Okay, so that was just a comment on this gamma modeling. Okay, so the next thing that was on the list was to develop a correlation between the boiling point and the molecular weight, and that's very simple now. So we have discussed that these what we will be doing in that case, we will be correlating the lower molecular weight boundaries that have come from the gamma distribution model. So these are linked to the gamma model sheet. And these are the lower molecular weight, lower boiling points, which are essentially the same as the boiling points, average boiling points of normal paraffin. So here we have normal paraffin compounds. We know their molecular weights, and we also know their boiling points. And these boiling points here, you see that big formula here. So these boiling points are estimated from the 2 correlation and the normal paraffin 2 correlation that's in chapter 5, and using the normal paraffin molecular weights. And this is just the normal paraffin molecular weight formula. The exact formula for normal paraffin, knowing the carbon numbers. So yeah. So we are just correlating these 2 numbers here and coming up with this PBM correlation for this particular fluid system. Okay, so we can start with the next topic we have, and the next topic is the initial EOS model development with the knowledge we have from the C7 plus characterization that we just went through. And so we know that in the equation of state model, we have actually 2 tables, right? So the one table is the component properties, and we now all have all the information on how to come up with those component properties, like TC, PC, eccentric factor. That's something we will also see in the Excel file. And the other is this binary interaction parameter table. And here, like, general recommendation is that you can start with the for Peng-Robinson equation of state model. We can start with these binary interaction parameters correlated with this default Q correlation, and for between the hydrocarbon and hydrocarbons, and for the SRK we can start with the binary interaction parameters of 0, and then in the tuning process we can change those accordingly. And for non-hydrocarbons, actually the values are recommended. Okay. So yeah, what we were going through now is this second table in the equation of state model. That's the binary interaction parameter table. The general recommendation is that if you're using a Peng-Robinson equation of state model, you can start with the default Q correlation for these hydrocarbon BIPs. For SRK, you can start with a 0, and then later on, when we start doing EOS model tuning, you can see what binary interaction parameters are needed, and you can change them accordingly. And we also recommend that when we are developing this common equation of state model, where all the samples and their associated PVT data is there, we recommend to develop a detailed equation of state model with the same resolution of component as we have from the lab, and the heaviest fraction can be a C36 plus fraction. This is to get the highest resolution PVT model, which we term as the parent PVT model. And this parent PVT model can be then used to create different child PVT models for the different application purposes. Like, for example, you can generate a black oil table with that detailed equation of state model. You can create a pseudo equation of state model for reservoir simulation. You can generate a relatively less detailed equation of state model for surface processing, But all these PVT models, all will be consistent among each other because they originate from the same parent equation of state model, which is tuned to very detailed PVT data. And also, if you have isomers, lab reported isomers for the C7, C9 components, we also recommend keeping them as is in the equation of state model development to better that will help to handle the changing relative aromaticity, paraphenicity among the different samples, at least for those components. So that was about the like how you can get this equation of state model tables, and that's something we will also see in this Excel file that we are using for this exercise. The second thing that is needed to do any EOS calculation is the composition. And we had a dedicated session on composition where we highlighted the measurement methods and also the associated uncertainties in those compositional measurements. And that's why we emphasize more on how you handle those compositions for doing EOS calculation. So here we know that the common equation of state model may have PVT data from hundreds of samples, and when we are defining the sample specific compositions in a common equation of state model, so these following points, they should be considered. We should be aware that the different PVT labs may be providing the different samples with different heaviest fractions. So that's something Gulnar mentioned. For example, one lab may have provided C20 plus, the other may have C30 plus and C36 plus, the third lab. And also the compositional data quality may vary from one lab to another. We may have distribution uncertainties in the molar distribution of CN plus fraction. We discussed the reasons for that. We may have uncertainties in the recombination ratio. And we should also be aware that the PVT labs, they only measure the mass fractions, and the reported mole fractions for these heavier fractions are usually calculated from some arbitrary molecular weights in the lab. So we should always honor the lab reported these mass fractions and calculate the the mole fraction using more representative molecular weights of each component. So what is the recommended workflow for coming up with the composition that we should be using in the EOS model calculation? Number one, use the lab reported weight fractions for all compositions. Then use the gamma model in this to replace any bad quality lab weight fractions in surface oil samples. And here it should be well-tuned gamma distribution model. And for that you need good amount of samples. If you want to have more confidence in your gamma distribution model, you use that model to replace any bad quality data in your surface oil samples. And also, together with replacing any bad quality data, you also need to split the lab reported heaviest fraction, which could be, for example, C20 plus, to the EOS heaviest fraction. So that could be your C36 plus for each of your surface oil samples. Meaning that if the lab has provided you the compositional data only until C20 plus, you would like to know what is the amount of C21, C22, C23, and so on until C36 plus in your equation of state model, because your equation of state model may have those components. And for that purpose, you need the gamma distribution model to split that lab reported heaviest fraction to the heaviest fraction of your equation of state model. And then you just recombine this surface oil composition that we have gotten from the gamma distribution model after doing these corrections and splitting from the lab reported heaviest fraction. you use this lab reported, you use this the flashed oil composition from the gamma model, and use the lab reported flash gas composition, which we believe have less uncertainty compared to the flashed oil composition. So we don't do any alteration in the lab reported gas compositions. So we use this lab reported surface gas, the gamma model calculated flashed oil composition, and then recombine them using the lab reported recombination ratio to get the total composition in terms of weight fractions. And this, we again know that this lab reported recombination ratio may have some uncertainty, and that we should consider during the EOS model tuning, that we should be able to change it slightly to modify the total composition. And then we calculate the ZI from the mole fractions from this calculated mass fractions here, using the molecular weights in the equation of state model. Not using the lab reported molecular weights, because now we believe that the EOS model molecular weights of the different components are more consistent and representative to the fluid system we have. And the average molecular weight is again simply the average molecular weight calculated with this with the mass fractions and the individual component molecular weights. And then once we have calculated these mole fractions, then use these mole fractions, which are now calculated after a certain process we have discussed here, in your equation of state model calculation, instead of using the lab reported ZI directly for your equation of state model calculations. So in the Excel file, again, we will go through this workflow of how we can calculate that composition, and it will be more clear. Okay, so you can just do this simple exercise here in Excel. Try to come up with the equation of state tables and the component properties, and see a binary interaction parameters can be calculated, and also the composition of the samples that we should use for the initial EOS modeling. Any questions so far?
Hafiz, will you show in the previous slide? Can you go back to the previous slide? One more. Yeah, this. Will you show us split lab report 2.2? Like when C20 plus 2 year.
Yeah, so this is so actually the two lab reports we have in this course, they have the same lab reported heaviest fraction C26 plus, and that's the same we have in the equation of state model. So in this exercise, it's not shown how you can go go from C26 plus, which is the lab reported heaviest fraction, to some higher fraction. That's not shown now in the Excel file, but we will see if we get time. Maybe I can try to show you how you can use that gamma model to go further.
Okay, thanks.
Yeah. Any other questions? Okay, so this Excel file. Okay, so now we finished with that correlation, and that's the same Excel file we were using before, G7 plus characterization. So now we jump to the next sheet. That's the initial EOS characterization, and here we can see we have the molecular weight, specific gravity, and boiling points. Those three things are needed for calculating TC, PC, eccentric factor, volume shift, and critical volumes. So for that purpose, what we have so we will see how we have come up with the numbers here. properties of C6. These are just taken from the, but you can use other correlations, or you can even use the gamma distribution model if it is tuned from C6 plus fraction, for example. But generally, the Cash-Rosabody properties are okay because the C6 component doesn't have any aromats. It has only naphthenic compound, and also it's mainly paraffinic. So that's why these component properties, it doesn't change much from one fluid system to another. But from C7 plus, this molecular weight, these molecular weights, these are coming from the gamma model. So you see that it's linked to the sheet, and we are taking the average of the component molecular weights from the two samples. So the average for C7, and it's an average of these two numbers, which is essentially 99, and the average of these two numbers, which is essentially 109. The only difference that you will see mainly will be in the Habeas fraction, where we have very different numbers, so 422 versus 509, and here the average value that we have taken is 465. And again, this Habeas fraction, we don't know what is the best component property for that particular component. So that is the most uncertain component in the equation of state model, and we try to this component is given the first priority when we start doing the EOS model tuning. We try to change its component properties first and see if things can get better. But again, you don't want to change the properties too much, because then you may affect the phase behavior calculations that you don't have the measurements on, like for example gas injection or miscibility, minimum miscibility pressures, for example, and near critical phenomena. So all these things can be affected. And that's why just changing we try to change this Habeas fraction by like plus minus 5% the properties, and see if things can get better. And then if they don't, and if we need more tuning, then we go for further tuning of the other component properties. And that's something we will see in the coming slides when we will discuss the EOS model tuning. So the molecular weights, these we have discussed that. And the specific gravities, these have come from the Tune-Soreda correlation. So yeah, knowing these average molecular weights here. And then the boiling points, they have come from this function that we have created here, 492.39, something like this. So that's being used here to get the average boiling point as a function of the average molecular weight. And then these numbers here, this TC, PC, eccentric factor, for example. So TC, PC, we can calculate, for example, equation 5.75 as a function of boiling point, specific gravity, and that's equation in the monograph. This is 5.77, and the reason why they are not shown here, because like for example the software we use, Basecom, it has this correlation built in, so it just spits out these numbers, knowing the specific gravity and boiling point given here. And it's the same, like for example, if you're using PVTP or PVTI, PVTSim, if you give these numbers, and if you have the options of using, for example, correlations, two correlation or Lie correlation, whatever correlation you want to use, you can use to come up with the estimates of TC, PC, and for example, eccentric factor. And then the volume shifts, again, these are dependent on the specific gravity. So what most PVT packages have now is that they will calculate a volume shift value for the given component that matches exactly with an equation of state model, the specific gravity given for that compound. And then critical volumes, these are only needed to come up with the estimates of with the binary interaction parameters that's stable to with the Chu correlation. So, and again, this is equation 5.76 in the monograph. If you look at the binary interaction parameter table, so we have these non-hydrocarbon components with the hydrocarbon components. Yeah, so non-hydrocarbon with all these compounds here. These numbers are given in monograph table 4.1 for both SRK and Peng-Robinson EOS model. So those numbers can be used from that. And all these hydrocarbon bits, generally we recommend correlating the hydrocarbon bits between C1 and C7 plus. So essentially everything will be 0 until C6 in this column. And then you will have some numbers from C7 plus. And then usually C2 to C26 plus, all these columns are generally all these columns are generally 0 initially. And for SRK, we start with the 0 hydrocarbon bits. So even the methane C7 plus bits are also 0 in SRK US, and then we see if we need any binary interaction parameters to better match the lab PVT data. And this is an important figure just to highlight why the C7 plus characterization is important. And again, you can see, so these diamonds here, these represent the Karswitzer-Body specific gravity for each carbon number. And this line here, this represents the average gravity molecular weight relationship for the fluid system we have. And you can see they are quite different, especially for these very heavy fractions. And also this black data is plotted with the black symbols here and the black line. This is the molecular weight. These are the molecular weights, and you see that the molecular weights that we have in the for our fluid system coming from the gamma distribution model, they are quite different than the lab reported or Karswitzer-Body data. They are different than the data reported by Karswitzer-Body, especially for these heavier fractions. And you will see the consequence of these different molecular weights on the compositions that we will just see in the next spreadsheet. Any questions here so far? The compositions. Okay. So now we jump to the compositions. Network quality. Yeah. So we have the compositions. So now here we have discussed the how we can populate the property. We can populate the EOS model tables with the C7 plus characterization work. And now the next thing is to come up with compositions. How we should be handling the compositions for calculating the for doing EOS calculations. So we have these are the component slates we have. So these are the component slates we have for our equation of state model until C26 plus. We have the molecular weights. This again coming from the previous sheet, the initial EOS characterization. This is the flashed oil, and so this whole table here, which I'm highlighting here. So this is for calculating the composition of the black oil sample, and we have the flashed oil, and this is the flashed oil composition from the gamma model. So these are the numbers until C6 until C6 component. The numbers are the same as the lab reported data because we didn't do anything on those numbers with the gamma distribution model. The gamma distribution model starts from C7 plus. So for C7 plus components, the amounts now come from the gamma distribution model. And the way they are calculated is because we know that if you look at, for example, this sheet here, which is referenced here, this gamma model sheet, if we go in this sheet and if we look at this sample 1, we know that these calculated mass fractions, these are normalized to total C7 plus in the lab data. Okay, so these are normalized to the total C7 plus in lab data. So we have to denormalize it by multiplying each of these numbers with the total C7 plus reported in the PVT lab, reported by the PVT lab report. So that's why you look at these numbers here. It is there is a sum of all the C7 plus components in this lab reported data. So lab component molar distribution model. So this is coming from that. This is the total C7 plus amount in the lab reported in the PVT lab report, multiplied with this normalized mass fraction calculated for that component in the gamma model sheet. And that's just dragging down until C26 plus. And then this lab reported flash gas, again in a mass percent basis, it's the same as the lab reported data. So this is just coming from the PVT report. Here we are not doing anything and just using the data as is. And then this is the calculated total sample using the recombination ratio from the PVT lab report. So this is the recombination ratio from the lab, 0.015337. That's what we calculated yesterday when we were doing the recombination QC of this composition. So that's just using the same formula of you remember Wi is equal to WOI times 1 minus FG plus WGI FG. Just doing the simple recombination to calculate the total composition in terms of mass. And then this is on a mole percent basis using the formula shown in the PowerPoint. Okay, so these are on a mole percent basis, and then this is the composition reported in the PVT report, which you could have used directly in the PVT package, and that's something we have come up with this workflow that we have presented. So this is for the black oil sample, and here you can clearly see how much difference it has made here. Like if you just compare the mass fractions calculated by us with the lab reported mass fraction, you will see that they are essentially the same. So for example, for methane, it's 3.54 weight percent, and if we go back and look at the lab reported data, I think it's not here, but if we just go back into the PVT report and see. Yeah, we can just no, it's like 1%. Yeah, so you see this is the reservoir fluid composition on a weight percent basis, 3.54 for methane. And if you look at this Excel file, 3.54 for methane. But when you convert these mass fractions to mole fractions using the molecular weights that we have now from this gamma model that's tuned to our GC data, you can clearly see now that the mole fraction, for example, for methane is now 33.9 compared to 34.7 that's in the lab reports, which is already about the 0.8-0.91% change. And it's a similar workflow used for the near critical oil. And here the difference between these two compositions are small. And when we will do the EOS calculation, we are going to use these two compositions instead of the lab reported compositions on a mole percent basis. So yeah, so this is the Excel file showing the same workflow that we went through in the presentation. Any questions so far?
No, just a question. Regarding the Sureda correlation, will you take that density instead of lab?
Yeah, so that's something we showed here, I guess. Yeah, so these diamonds. These are the specific gravities of the components from the lab data, which is cut for the body, right? And we know that that's that the cut for the body data. It was measured for some fluid system, and our fluid system may not be the same as the fluid system they have used, for example, for their measurements. So that's why we have come up with this correlation, which is now the Sureda correlation. That's this blue line here, which is tuned to our data, and we have only 2 points here, the C7 plus specific gravity and molecular weight. And so we will use the specific gravity given by this solid line. And again, the litmus test of this specific gravities that we will get from this correlation will be how good or bad are the surface oil densities predicted by our equation of state model. So we will see with the equation of state model package, like if we use this equation of state model with the gravities coming from this solid line, how the surface oil densities, the lab reported surface oil densities are calculated.
Okay, thanks.
Very good. So I think it's time to go back on the that's. So the next thing and this next thing on the exercise is to look at the predictions with this initial EOS model that we have developed in this Excel, and to do the predictions of all the PVT data. So we have the 2 PVT reports. We have a series of experiments, CCE, DLE, separator tests on black oil, CCE, CVD on the gas condensate, and we also have saturation pressures. And to do the predictions of that PVT data, we need to have some kind of PVT software or PVT package. And we internally use FaceComp. So, and there are very few people actually that use FaceComp. So that's why we will only show the output file of FaceComp. But if you want to try using FaceComp, you can actually download it from Zix Technology website. If somebody wants to is interested in downloading it, just let us know and we can send you the link of the website. You can download it and you can use it for 1 month. It's a free license for 1 month, and afterwards you just have to buy it. So if we go to the so the FaceComp file. So you can see this is a FaceComp file, and then this is the input file. So it works and just like for example Eclipse works. You create a data file, you run it with the simulator, and then it creates an output file. So we will read through the output file and just try to look at the predictions of I don't know if it's too small. I can just sorry. Maybe it's much better now. So first, if I open the output file and if I just show you the characterization here, maybe I can also show the input file just to show you what was given to FaceComp. It's also this one. Okay. Yes. So in the FaceComp input file, so that's the .FaceComp file, and we provided for this C7 plus fraction, we provided the molecular weight, specific gravity, and boiling point. and then it filled this whole table with the correlations that we mentioned in the Excel file, and those are also given in the SP monograph, and we have given reference of all the equations in the SP monograph, and also this binary interaction parameters. So these numbers, non-hydrocarbon with hydrocarbon BIPs, these come from this table 4.1 in the monograph, and these hydrocarbon BIPs, these are kept 0 for the SRK EOS model that we are going to use. So that's just for the orientation. So now if you look at the output file, you see all these numbers fill in. So we provided this column, this molecular weight, specific gravity, and boiling point, and then it has come up with the numbers for TC, PC, eccentric factor, volume translation, critical volumes, and the EOS model that we also saw on this Whitson PVT. And for initially we have this 0 binary interaction parameters between methane and other hydrocarbons. And if you go for the experiment, so we just search for experiment. Why my life is so complicated. Okay. Yeah, so if you go to the experiment, you can see that there are, so the first experiment is actually the separator flash of the recombined sample. So we take the recombined composition and flash it to the same separator condition where the samples were taken, the separator oil and separator gas, and we are just comparing the measured and calculated and the lab reported quantities. So the liquid molecular weight at separator condition, that will be the separator oil molecular weight, the density, and you can see separator oil densities are very accurate here. The GOR, we should expect a good match on the GOR if the separator samples were in equilibrium, and we saw it was they were in very good equilibrium with this Hoffman QC. And then we should expect to have a good match on the separator composition, which you can see here that this is C1Y, that's the methane content in the separator gas. And if we go down further, for example, this is the multi-stage separator test for the black oil sample. And you can see, for example, the total GOR, very good match on the total GOR. API is spot on. And again, as I said earlier, that the litmus test of your C7 plus characterization, especially this molecular weight specific gravity correlation, is that you should have a very good match on your surface oil density. So you see stock tank oil density very accurately predicted. And yeah, and then this is the shrinkage factor, for example, of your or the BO of your reservoir fluid. Let's leave that now.
Bilal?
Yes.
One question on the, do you take special consideration that the oil-based MAD is between C12 and C20 when it comes to the molecular weights uncertainty? I mean, those are the ones that have been most affected, right?
You mean the molecular weights of the components between C12 and C20?
Yeah.
Yeah. So I think that's something Curtis he mentioned. Like if we are using the contaminated samples for example for EOS model development, then what we try to do is we try to have a separate set of components that represent the oil-based mud components. And then we have a separate set of components that represent those components in the in situ fluid. And for the in situ fluid, like the components that we have for the oil-based mud, we generally consider them as normal paraffins. And then for these other heavier for these fractions that are part of in-situ fluid, there we come up with the molecular weights and specific gravities from this, for example, Sereda correlation and the gamma model.
And what will make you decide whether you work with contaminated fluids or you work with uncontaminated and you add on top the oil-based mud?
That I didn't understand the question, sorry.
Whether to include the PVT data and tuning for contaminated samples.
Yes.
Yeah, it's like if it depends on the amount of PVT data of high quality that you have for uncontaminated samples. If you have a lot, then we would tend not to include the PVT data for contaminated samples. If you don't have much or any good PVT data for uncontaminated samples, then you have no choice.
No.
So we always will, I mean, if a significant amount of all the PVT data is on contaminated samples, right, let's say even 50%, we would probably do the EOS modeling on only the 50% PVT data without contamination. But then we would turn around and do predictions for the other 50% of the PVT data as just predictions, including an oil-based mud description in the EOS. In other words, we just add components for the oil-based mud, add the amounts of oil-based mud the lab says we have, and then predict. But if you start seeing some deviations there that you don't see in the tune data for uncontaminated, we don't worry about it. We would assume that it had to do with the accuracy of the EOS model for both reservoir and a mixture of reservoir fluid and the oil-based mud. That's only if you have enough. I mean, you would only take that extra exercise and check that if you had quite a bit of that data with contaminated samples.
Okay. Yeah.
So this is a long answer, but I mean, that's a little bit the same I tried to say yesterday. So.
Yeah, but it's clear. Yeah, thanks.
Okay, so now we looked at the PVT data at low pressures, like the separator test, single stage flash, or the separator oil. Everything looked there very nice, and that's what we expect from the initial EOS model that we have developed after very thorough work on the C7 plus characterization. And at low pressures, your K value should be reasonable, and all the data at low pressures, all PVT data should be reasonable. And at high pressure, if you look at, for example, the CCE experiment, what we see, for example, on the saturation pressure, that we have about 11% deviation, which is unacceptable for saturation pressure measurement. And also, if you look at this near critical gas condensate, we have the calculated liquid dropout represents that this fluid is an oil. So you have 100% oil saturation at, for example, at all pressures higher than the saturation pressure. So it is predicted in this as a bubble point, which you can also see here. But we know that it's a gas condensate and it's a near critical gas condensate reservoir. So at high pressure, the K values requires tuning, and we will see how we can achieve that. But if we look at, for example, the other sample, which is the black oil sample, and here again we see that the saturation pressure is off by about the same magnitude and in the same direction, which is also a good sign in terms of the EOS model tuning, because we know that if we will change, for example, binary interaction parameters. So I mentioned earlier that if you will have a positive BIP between C7 and C7 plus, C1 and C7 plus, it is going to increase the K value of methane, which is going to increase the bubble point, and that binary interaction parameter is going to decrease the K values of C7 plus fraction, which is going to increase the dew point pressure. So if we will have just the positive BIPs between the hydrocarbon in this equation of state model, it is going to move the saturation pressures both in the bubble point and the dew point in the same direction, and we will see we should be able to see some good predictions there. So in essence, a good initial equation of state model should be reasonable at low pressure and temperature conditions, and may require slight tuning at high pressures. That's something we will try to achieve in the next session. Okay, so I think the next topic on this is EOS model tuning. So we have an initial EOS model that we would like to tune, and so just some theoretical stuff here. So the objective, what equation of state model tuning means is that you try to minimize some kind of objective function. So you try to minimize a root mean square, which can be formulated differently in different PVT packages. But what you try to achieve there is actually try to minimize the difference between the calculated data and the lab reported or the expected data, and you control your RMS actually with these weight factors here. You define weight factors for different different kind of PVT data, and the weight factors, they actually depend on different things. So number one, how is the quality of PVT data, and there are different ways of evaluating the quality of PVT data. We also went through some of them. The relative importance of a certain type of PVT data, for example, saturation pressure, is considered usually important because the different types of PVT measurements or reported PVT data are actually referenced to the saturation pressure. Let's say, for example, VRO, the relative oil volume, is the oil volume divided by the volume at saturation pressure. So if your saturation pressure is predicted wrong, the volume at the saturation pressure will be predicted wrong, and then the VRO curve may look wrong. So yeah, and also how severely a certain type of PVT data is affected during EOS regression. For example, saturation pressure versus gas Z factors. That's one example. Or gas Z factors are usually not affected when we change the EOS model development, because when we change the EOS, when we do the EOS model tuning, because the gas Z factors, they are mainly affected by the volume shift of these lighter components, which exist in more amounts in those gases. And how many of a certain kind of PVT data exists. For example, in an SEC experiment, you may have 1 point for the saturation pressure, you may have 10 or 15 or 20 points for the liquid relative volume. So you may want to weight saturation pressure more to give it the importance either same or higher than the liquid relative volume. What variables do we use for EOS model tuning? So if we just take an example for just a theoretical example, that if we have NC number of components in the EOS model, which could be like, for example, 40, 50 if you have a detailed equation of state model, and if we have NS number of samples, here in this case we have only 2, for example, the number of component properties variables, it will be 5 times NC, because we have 5 different properties for each component. We have molecular weight, TC, PC, eccentric factor, or you can use the boiling point and the volume shift. So we have 5 properties and the number of components NC, so it's 5 times NC, the number of maximum possible EOS component variables. And then the binary interaction parameters, the number of maximum possible variables could be in this, because this is representing this lower diagonal of the binary interaction parameter matrix. And the number of compositional variables would be ns, that's the number of samples, times the number of components, -1, because we know that the sum of mole fraction should be equals to 1, so it should be 1 less than the number of total components in the EOS. So if we take one particular example, for example, if we have 10 number of samples and 50 number of components, the total possible variables could be 1965. That's a huge number. Where 250 actually comes from this 5 times NC, and these are your binary interaction parameters, and then this is the compositional variables. So one important task in the EOS model building is to minimize the number of variables used in the regression. So you try to find what are the best variables, best minimum number of variables or most effective variables that you should be using in the EOS model tuning. And so the way we achieve that is actually we know that the EOS component properties are usually not changed for pure component. That's something we know. And also we know that a good starting equation of state model should guarantee reasonable estimates of volume shift and the molecular weights, because those are actually coming from the volume shifts. They ensure that your average component gravities are consistent, and the measured flashed oil, for example, densities and molecular weights, they are reasonable with your equation of state model, the initial EOS model. So these generally we do not change during the EOS model tuning. And we also consider that the TC, PC, and these boiling point or eccentric factor, they have to be changed in a consistent way. So like for example, we should try to keep the monotonicity of the TC, PC, and boiling points with respect to the components, and that's why we try to change them with very limited variables for these heavy fractions. And so that's why this component property for all these SCM signal carbon number heavier fractions, they are usually changed either with a constant multiplier to keep the monotonicity of those component properties, or we can also do ramping. That's not something that you can do, for example, in other PVT packages, but FaceCom allows it. So, but the maximum, as a rule of thumb, the maximum change is usually 5 to 10% from the initial values, if the initial EOS model is properly characterized with the C7 plus characterization workflow that we went through. And the boiling points, we generally try to avoid changing boiling points, because these should be constrained by the normal paraffin bounds. That's something we have discussed, that the C7 boiling point should be between the normal C6 and normal C7 boiling point. And generally this constraint is very narrow. So we generally try to avoid changing boiling points. So we have only, for example, TC and PC mainly as a regression variable together with the binary interaction parameters. And this heaviest fractions properties, so N plus, which could be our C36 plus, that we know is the most unknown, and also can be slightly different from one sample to another. So it may need some more change in the component property compared to this single carbon number fraction. And generally it is considered as a separate variable from the single carbon number fractions. This is just an example of what is the difference between a ramping multiplier and a constant multiplier. So this blue line is a constant multiplier where you change all the component properties by the same magnitude or same multiplier. So here it's like 5% change. And this ramping multiplier, that's something we can have in, for example, FaceCom, where you generally you allow the change in the component properties more and more as you go towards heavier fraction, because we know that the uncertainty in those component properties increases as we go towards these heavier fraction, and it's less when you are towards the lighter fractions. The compositional variables, so the compositions that we have gotten in our initial EOS model, generally those are adjusted by two regression variables, recombination GR, because we know that the FG that we have used from the lab data for the recombination, it may have some uncertainty, and the amount of the heaviest fraction. And there are many reasons why you would like to change that. One reason is that we know in this, if we are developing a common EOS model, we have a single CN plus component, and it has a single, for example, molecular weight. And we know we already saw, for example, this gamma distribution model, that the molecular weight of that heaviest fraction was different from one sample to another. So that if we have the common average molecular weight of that heaviest fraction, that can lead to some error in the mass to mole conversion for this heavier fraction. So that's why you may need some adjustment in the CN plus amount, the heaviest fraction amount, while tuning the EOS model. That's one reason for changing that. Okay, and then we have the binary interaction parameters. They are usually changed over the initial values, and these are kind of the magnitude we usually change. For example, for C7, for single carbon number fractions, for the heaviest fraction, it could be slightly higher. But again, if you have very small amount of data, and if you're only changing, for example, the binary interaction parameter between C1 and the heaviest fraction to match your data, you have to be careful and not to change the amount, the magnitude of this binary interaction parameter too much from the initial value, because that may lead to some non-physical behavior or some very strange predictions of the PVT calculations outside your measured PVT data range. Yeah, so the way we do the EOS model tuning, that we try the different combination of the variables, and then see which combination best matches the lab data, provided that the change in the change in the variables used for the EOS model tuning is not more than the limits we usually have as a rule of thumb from the initial values that we have in the EOS model. And also weight factors, they are also changed along the way the EOS model tuning is done. So it's not a straightforward process, and it requires experience, and certainly it's not just the push of a button that you get a tune equation of state model. And you have quality of the data, that the tuning time may take from weeks to months, or so it is a time-consuming process, and it has to be done diligently. And when we are saying that the compositional variables are changed, and the compositions are slightly adjusted with, for example, these two variables, the maximum change is usually not more than 1 mole% in the methane content of the reservoir fluid. So that's just like a rule of thumb for us internally, and usually it's less than 1 mole%. This is just an example of how the tune PVT tune equation of state model can look like compared to the initial EOS model or the different PVT. So this is saturation pressure measured from a swelling test, for example. This is a liquid dropout or the liquid, for example, shrinkage. This is viscosities. Viscosities we haven't covered yet, but we will do it. That's the next thing on the list. And this is, for example, liquid dropout from or from a very near radical gas condensate. Okay, yeah. So that's just the key takeaway. And that's the most important thing. Never as easy as pushing a regression button in a PVT package. So. Curtis, your 2 cents on this topic, the tuning of EOS model.
Well, it's the best analog for those who are petroleum reservoir engineers is that of doing a comprehensive history matching of, for example, a water flood for 100 wells, 50 wells, 20 wells, whatever you have, where you expect the reservoir model to predict the pre-water flood gas oil ratio, pressures, for all the wells, and then after the flood starts, you get the water cut coming in, and it's a very complicated work process. It's something that takes time. The big advantage of doing proper EOS characterization and modeling with multi-samples and comprehensive data is that you typically don't have to redo the process. You can simply QC the accuracy when new samples, new PVT data become available, that the EOS is still predicting accurately, as opposed to history matching of well performance. So it's a comprehensive, longer process to do it really right. Once you get sufficient data to really do it right, you may have a preliminary EOS where the exploration well, maybe delineation well, provides a few samples, and you get PVT data, and you can build an EOS model that's not as reliable for the life of the field, but can be used for initial assessments. But may need to be revisited as you get more samples, more PVT data, for example. So I think those are the main takeaways, that the process is tedious. There's a lot of data. There's a lot of types of data. There are a lot of, let's say, physics model parameters in the model that are not familiar, used on a day-to-day basis, like permeability, porosity. And so doing this work requires also this period of training, which of course this course is part of. But if you have even with the training and understanding, you simply have a hard task in front of you and need patience and diligence and turning all the stones several times to make sure it's done properly. But once done properly, then we feel at least strongly that you can write off that for this field, you have an EOS model that can be used throughout the life of it. That's the goal.
Carlo?
Yeah, it's more. I'm trying to understand. So when I look at subsurface projects, we tend to work a lot with the low, the mid, and the high across several disciplines. Geophysics, petrophysics, name it. My question is it why did we don't work with an equation of states that it highlights this difficulty, meaning that you might obtain 3 matches that they are equally appealing to you and might produce different results. Now, the question is it because we in the oil companies were too naive and we think that whatever you give to us is so good that it doesn't have variability? Or is it because the people doing equation of states, they have historically given only one equation of state, which implies that you think that's the only one that you can have. What's the take on that? Are we naive, or will you just spoil us by just giving us one answer?
Well, no, I'd be more honest than that. If you have a case with, let's say, 2 samples, 2 sets of PVT data, we build an EOS model and feel very that we've done a good job of that. Okay, and we give you 1 EOS, and you say, well, how unique is this? And I say, well, if you would have given it to us on another day, or if I would have had one of my other engineers do the work, or maybe it's a non-unique solution with so few data. You might have, I like to say, if you've got 2 samples, you might have 10 EOS models that match that data equally well, but that are, different, if not markedly different. Okay, 10 different good engineers doing this. But as you go to 10 PVT samples, you take the same 10 experienced EOS modeling experts, you give them all 10 of those and start coming back. Well, probably 4 of them are going to succeed in getting all 10 samples matched well. The other 6 are not able to because of either the software they're using or the patients. Their boss says they're going to get fired if they don't deliver something, etc. So only 4 succeed, but you still have 4 EOS models that are describing 10 PVT samples, and you're starting to get a more unique set of EOS models. But if you go to that next step and you've now got 50 samples and you got gas injection processes, you got a really complex set of data, then I would say that those 4 engineers, maybe 3 of them come back after 6 months of work or 6 weeks of work and have a really good match of most all the data. They've done it independently. What I would say is that if you go through that, those 3 equations of state, if you start predicting outside the massive amount of data you have, the predictions are not going to be that different. And then interpolating within the vast amount of data you have in those 100 samples, you're getting more or less equally good results. So you basically have come to 3 different models, but they're more or less the same quality for doing the job. And then you have a much more unique, what I would call that, those 3 are all, you can pick and choose as you like on a given day, and they'll give you essentially the same results. So you've got a model, any of the 3 you could use forward and not have to turn around, I think. So I think that's the process of it. It's not unique until you have a lot of data of a very wide variety being tuned to an equation of state with some expertise, with some patience, and certainly with some time involved. Okay, I don't know if that answers your question, but we're not trying to sell you uniqueness with 2 samples, no.
But do you think, of course, do you think that when we sanction our projects is with 1 well many times or 2, and maybe we don't have a DST, so should we be asking for at least 2 different models, so we understand what we're working, what we're going into, what we're getting into right before sanctioning in terms of uncertainty from the PVT side?
I don't think so. I think the better way to go about it is you get the model after 2, you get another well or 2, you get additional PVT data, and now you got more uncontaminated data, PVT data. And at that point, you sanction a QC of the original equation of state. You basically see how well it's doing with all the new sample PVT data. The answer will likely be not as well as you would like, so that you need to do a revision of the EOS model. If you're lucky, it's still doing a good job on all the new samples. I would say that you work that way. You start with 1. you QC it, you revise it. Of course, that version 2 of the model is going to be different than version 1, but you include all the data that was in the first 2 samples together with all the new data, so that version 2 is a comprehensive cumulative model. And then you might do that in 2 or 3 steps during the development of the field, and you're ready to put the well on, or you've had the field on for a while. So that's the way all big projects have been done properly. They have EOS version 1, 2, and maybe 3 if it's really getting complicated with gas injection, miscible, complicated compositional gradients, etc. You might have versions 1, 2, and 3. But all along the way, you can collect a new sample, QC it, make sure you're still doing well. That I think is a better approach.
Okay, thank you. Thank you.
And then, I think that's also, Curtis, for the commercial projects that we do, something that is essentially what we're doing, right? If we, you get the preliminary EOS with a limited number of samples, and then you get more data, and after a couple of years, you do maybe an update on that based on that new data, such that you have a kind of like a version control, a systematic version control of a model that just gets more and more verified. Kind of the extreme case of that is if you take that to the other extreme, where which also has been a case, I think, with a few of our colleagues here, Curtis, and probably yourself as well, when you come to fields where there's been like 20 different equations of state made, and nobody knows who made the different equations of state, what data was it matched to, which equation of state should you actually use. I think on that note, it's also equally important to if you have several equations of state, to have a very good version control of what equation of state should be used, what data was it matched to, and which version are we actually now using in the different to create the different Blackwell tables or for surface processing or whatever that application might be.
Yeah, no, that's right. It's better to have 3 versions over the life of the field than to have 30 models that have fit 30 different wells at different period points in time, none of which you feel comfortable using for anything other than that well.
And also on that, another call it a complexity on that note is not related to the EOS model itself, but also to the fluid initialization part, which in many cases are just done once and kept constant throughout the life of that field to not change maybe reserve numbers and these things, and it's not all the time included in for instance, uncertainty analysis and creating these probabilistic values as P10, P50, and P90 values, which is actually something that's fairly common to, at least that we advocate, at least for these shale reservoirs, where that's a huge uncertainty actually when it comes to the fluid initialization, what fluids you have down there, to be able to actually change that dynamically as one of those parameters.
Yeah, that's right.
Gulnar?
Yes, Hafiz, before we go to the viscosity tuning, may I confirm with you if I understood everything correctly?
Yeah.
So in the Excel sheet, now when we're building in any software the PVT samples, we have 2 samples. We enter molecular weight, which is from the, if I open the composition, there is a molecular weight stated in B column. So I copy that. I copy F column, calculated BO that we have mathematically corrected. I copy that, and I copy SG from Sereda correction, right?
Yeah, so you copy this column, you copy this column, you also copy this column, the D column. That's
okay, we don't have a true boiling point, but okay, yeah.
Yeah, but boiling points, yeah, like if you have already calculated these values from the correlation that are mentioned here, So then you don't need boiling point in your EOS package. So then you just need molecular weight. You only need the TC, PC, and eccentric factor. You can calculate, for example, there are also correlations in chapter 5. And you will need specific gravities to get the volume shift. So you need this, you need this, you need this, you need this, and you need this. And this should be calculated by the PVT package.
Okay, I just trying to apply it in the PVT sim. All right, then. So basically, what we're saying that we trust on our mathematically calculated values. We disregard the lab reported values, and we basically start working with that, and then we can tune the TC, PC, eccentric factor in PVT sim. Basically, start tuning those, right? That's how we should proceed.
Yeah, you can tune the CPC eccentric factor, or you can tune the binary interaction parameters, whatever you think is more appropriate.
And we shouldn't basically then tune on molecular weight, on composition, since we have already kind of QC'd it, and we basically looked at all the samples that the field has sampled. We shouldn't touch them and tune them again, because kind of we're double doing it. If we do all the procedures that you went through, then we should trust them, right?
Yeah. So the in terms of the compositions, what the procedure we went through is that we QC'd the composition with the gamma model, right? And then when we are doing when we are calculating these compositions here, which is column F and column K, we are using the lab reported recombination ratio. So we are using these ratios here, right? And this is from the lab data, and we know that this may have uncertainty because these are related to the GOR, the recombination GOR, which is about plus minus 5% uncertainty. So you should try to change these numbers, but PVT sim doesn't let you change these numbers. So that's the unfortunate thing there. And so what in that case, what you can try, if you have only 1 or 2 samples, then we generally don't change these 2 numbers here. But if you have a lot of samples, like 10, 50, then you should consider changing these 2 numbers here from the lab data. And in that case, you can just try different combinations in PVT sim, like do it in Excel. Just try different scenarios, get different compositions with different FG values, and see which one gives you better prediction.
Okay, and then in PVT sim, then I should be only starting tuning PC, TC, and eccentric factor.
Yeah.
All right, thanks.
Yeah, the binary interaction parameters, if you have them, yeah. Okay. Yeah, but the other important thing that we will go through tomorrow, like once you finish the US model tuning, then you should try to QC whether quality check whether you have done the US model tuning the right way. You have to check whether the final model is thermodynamically and physically consistent. That we will go through tomorrow. But before we finish this US model tuning, I just want to show you the results, and then Matthias will take over. He wants to show us, give you some good exercises for the evening before you go to sleep. Yeah,
that's how you will sleep.
Yeah, that's how you will sleep. That's right. So on the US model tuning, so what I'm gonna show you now that what we saw in the initial US model, that we have everything looks good at the low pressure and temperature side, and on high pressures we needed to tune the K values, and in the US model tuning, so that's this is the output file phase.com, where we have tried to tune the US model. And what is done there from the initial US model, we have now added some binary interaction parameters between methane and C7+, and there is nothing else changed in the EOS model. So all the component properties, PC, TB, PC, eccentric factor, these are all the same as initial EOS model. The only thing we have done or we have added here is some positive smoothly varying binary interaction parameters between C1 and C7+. So these were correlated from this Q correlation, and then we just regressed on the binary interaction parameters with one constant multiplier, and they changed from the initial values. So there was just one variable changing all these binary interaction parameters with just one multiplier. And now if you look at, for example, the predictions, so if you go to, for example, the separator test, which is representing the K values at low pressure, then you see this GOR that didn't change much. So it was about 297, and still it's about 297. The densities are not affected. So you see you still have a very good match at low pressure K value data, because by these binary interaction parameters, they are not, they have a very large impact on the K values at high pressures, and doesn't affect much at the low pressure value. So if you now go to the CCE experiment, where we have the K values at high pressure, the data representing K values at high pressure, here you see that, for example, now we are calculating the right saturation pressure and the type, the dew point, almost spot on with these binary interaction parameters. And also you see that the liquid saturations, they are very reasonable with the lab data. And the densities, yeah, they are also good. And if you go to the black oil, so again here you see that we have matched the bubble point quite well, about the same magnitude. And we have this liquid shrinkage matched quite well with the lab data, and also the densities are very reasonable at reservoir conditions. So yeah, so this was about the EOS model tuning, and the next topic is viscosity tuning, which we have to take tomorrow. So there are only 3 small topics left in this current PowerPoint, and that should not take more than an hour, and then we will discuss the EOS model application also tomorrow. So now, any other questions on this topic before Matthias will take over here?
Okay, let me see the screen. Yeah. So just as I'm going to try something a little bit. There's a question. We'll do the question first.
Any risk of over tuning? Yeah, so that's something what we tried to mention before, that if you have very small number of samples, 1 or 2, then you should not try to change a lot of parameters to get a good match of the lab PVT data. So in that case, you just, like, for example, if you have a very limited sample and if you want to match some data, just like bits are one variables that you can choose to change. But again, if you are changing binary interaction parameters from the default value, just change it very slightly, like very small numbers, and we have given the rule of thumbs at what are the expected values or expected range. Or you can change, for example, the properties of the heaviest fraction, which is the most uncertain. And as you get more and more PVT data and more complex PVT data, then you can start changing other PVT other component properties like single carbon number properties, etc.
Trying to like tune as few parameters as possible,
yeah.
That creates the greatest change in predictive capabilities is kind of a goal.
And also we will look at tomorrow like how to do the QC of the final EOS model. That also gives an idea whether you have over-tuned the equation of state model and have gotten a good match of the lab PVT data, but have generated an inconsistent PVT model.
Very good. So tomorrow, after Bilal will finish that part, we're going to do a course summary. So we're going to try to condense the whole week into like 30 slides or something like that. It's a pretty interesting exercise. but hopefully we can try to connect the dots of everything we talked about, so we understand why we talked about pure components on Monday, and tie that to what we've been talking about the last couple of days. We're going to leave that topic and look at different parts of where an equational state is vital to use for different engineering applications. So we, on that note, Curtis will actually go through a little bit more in detail this recovery factor of oil versus fluid type plot. And then we'll dig into black oil table generation, gas enhanced oil recovery, fluid inertization will be covered by Curtis. And then if we have time, and then we'll also cover separate oil shrinkage. But as a preparation for tomorrow and why we're going to end the session earlier today, we'll try something a little bit different where this is kind of a little bit more homework, but it looks a little bit frightening, but it's actually very, very straightforward if you just read different questions there. The intention is that you
don't see what you are showing.
Yeah, so I just asked, let's see. You see this? There we go. So I'll send out this email, and the intention is for everybody to just go into the software, the courses.wits.com, which is essentially made for equational state utilization purposes, and we're going to look at some common ways of utilizing an equational state, and we're going to also tie it to the different things we've been learning this week. And the list looks a little bit maybe overwhelming, but just do it step by step, and I think it will not take more than maximum probably 30 minutes. When we look at the different tabs here, when I talk about the fluid models tab, the fluid definition tab, the black oil table tab, everything is referring to the tabs in the navigation panel here to the left in the menu. So the fluid models tab is this one, the fluid definition tab is this one, the black oil table tab is that one. And if there's any questions related to this and to the exercise, just shoot me an email whenever, and I'll answer right away. And as I said, just follow the question step by step and reply to this email that we're sending out with just some quick answers to each question. Not reply to everybody so that the people can copy paste. So just reply to me, and we'll use that as a basis for tomorrow. And it's kind of like an inverse way of teaching, where we're going to do an exercise before we're going to talk about some of the topics. But that can encourage at least a little bit of stimuli and maybe interest of learning the key concepts and vocabulary for tomorrow.
Okay, so I think we can get started with today's session, the last session of the course. Oh, sorry, not the last day of the course, not the last session. And so today, like yesterday, we went through the workflow of EOS model development. C7 plus characterization was the main topic. And then the initial EOS model that was developed using all the data that we had, all the data that we developed or calculated using the C7 plus characterization methods. Whose microphone is on?
I think Curtis's microphone is on. I'll just mute you for a little second. Thanks.
And then we went through the EOS model tuning, and now today we will go through the viscosity tuning. And Matthias briefly mentioned yesterday that viscosity tuning, we do the viscosity tuning after finishing the EOS model development, where we tune the equation of state model to all phase behavior type PVT data, like in liquid relative volume, saturation pressures, all other PVT data except the viscosity. And the reason why viscosity tuning is treated separately after finishing the EOS model development is because the EOS, the viscosity modeling doesn't affect the space behavior calculation using this LBC correlation that we are going to discuss in the next slide. So yeah, so that's something I mentioned. Like tuning viscosity model is generally done after the finishing the EOS tuning to VLE type data, and it doesn't affect the or alter the vapor liquid equilibrium type calculation, and you will see why that's the case. So the different viscosity models that are available are the LBC model, and then we have the Peterson model. And the LBC model, it's computationally faster, and that's usually preferred in this in like when we use the equation of state models usually for reservoir simulation studies. But one thing that we should be aware of is that the Peterson correlation is claimed to be better than LBC when you are predicting the viscosity. So if you don't have any viscosity data and you just want to do the predictions of the viscosities of your fluid model with some kind of correlation, then Peterson is generally claimed to be better than LBC. But we will see in the coming slide the workflow that we use for viscosity model development. We actually that workflow actually makes the LBC model also quite predictive. The prediction capabilities of the LBC model also gets enhanced through the workflow that we are going to discuss and we use internally at Whitsun. These are that's how the LBC correlation look like. That's question 3.133a in the monograph, and what you can see mainly from this equation that the viscosity here, it's a function of reduced density or the density of the fluid, and it's a fourth degree polynomial, and then we have these different coefficients. So 1, 2, 3, 4, and 5, and these are the coefficients default values in the LBC correlation. And generally, when people start doing the viscosity modeling, they generally tune these coefficients in the to the measured PVT data. But the way we do the LBC model, you will see that we generally don't need a lot of changes in these default values. And one reason you should avoid changing these coefficient values is because this is a fourth degree polynomial, and if you start changing, for example, this coefficient here or this coefficient here rapidly, it changes to match, for example, your oil viscosities only. It will change the shape of the polynomial curve rapidly, and it may start affecting, for example, densities that are not part of your fluid system, like that are not measured for your fluid system and are relevant for your reservoir condition. For example, they may rapidly change the gas densities that are on the other side of the density. And in this LBC model, so we have this reduced density, that's the function of density, and the critical density. And this is so you can see that the predictions of the viscosities are also dependent on how well the densities are predicted for a given fluid system. And then this function this function and this parameter here, that's the function of the pseudocritical pressure, temperature, and the molecular weight, and these properties, these are just calculated for the entire mixture, knowing the composition. So one reason why the LBC correlation has prediction capabilities very poor. The reason is that the LBC model, it uses these critical Z factor values, which you can see here actually, that it is using these critical densities, which are essentially the molecular weight divided by the pseudocritical molar volume, and pseudocritical molar volume, it's pseudocritical volume of it comes from actually this case mixing rule of knowing the pseudocritical volume. So that's just the sum product of VCI times UI, that's the composition. And then this pseudocritical volume, so that that can be related to, for example, the critical Z factor. You know that PV equals 1 ZRT, so that the critical volume or critical Z factors both can be used in the LBC model to calculate the pseudo-reduced density. So that's why we have this critical Z factors in the equation of state model. So yesterday when we looked at this table, equation of state model table, and hopefully you had seen it yesterday when you were doing the exercises that Matthias mentioned, that there were two sets of critical Z factor. One was this, and the other was ZC vis. So there were two columns of the critical Z factors. So this Z factor, we mentioned earlier that it's not used for anything in the equation of state model development. This was only used to get the Kij estimates, for example, from this Chu correlation, because that's function, the Kij from Chu correlation, that's a function of the critical volume and critical Z factors. But these Z factors, these are used in your equation in your LBC model or the viscosity model, and that's why, like, we know that the critical Z factor, it's not used in any equation of state calculation. So if you want to use EOS models, for example, vapor liquid equilibrium calculation, we only need the molecular weight, TC, PC, we need the centric factor and the volume shifts and the Kij. So you don't need and Kij you can estimate from the critical Z factors, and then they are independent of the critical Z factor. Once you have estimated, you can change them independently. So these are the component properties you need, for example, for doing EOS calculation. So when we change the critical Z factors, for example, or calculate them, for example, in some other way in the equation of state model table, it doesn't affect your equation of state type calculation, like vapor liquid equilibrium type calculation. But now, since the LBC model uses these critical Z factors, the predicted capability of the LBC model is generally poor, because the estimates of the critical Z factor that we generally get from some correlation, like, for example, we discussed that critical volumes or critical Z factors, they can be estimated, for example, this 2 correlation that's in the chapter 5 of the monograph. So those estimates are generally not adequate to give you a well-behaved viscosity model through LBC correlation. And one reason why it's not those numbers, like these critical Z factors or critical volumes from the default values are not adequate, is because if you start calculating the individual component viscosities with the LBC model, so let's say this is, for example, and this is your C7, this is your C8, C9. So if you start calculating for individual components, the viscosities at some higher temperature or even at the standard condition and the standard pressure, and you plot them versus molecular weight, what you will find out that with using those default values of critical Z factors or critical volumes, the component viscosities behave like this function. So it increases until certain point with respect to the molecular weight, and then starts decreasing again. So it is. So that's something you get actually in the non-monotonic behavior for the viscosity, and that's not physically acceptable, because we know that as the component gets heavier and heavier, the viscosity of all of that component should also increase. So that's why, like if you are doing viscosity modeling with the LBC correlation, what generally people do that they use the default values of the critical Z factors, and they just tune or change the different coefficients of the LBC model to match their measured data. But in that case, even though you could have gotten a good match of your measured viscosities, oil viscosities or maybe gas viscosities, but the model itself may not be physically consistent, because if you would calculate the individual component viscosities, you would find out that the individual component viscosities would be behaving like this as a non-monotonic function of the molecular weight. So to avoid having this kind of non-physical behavior in the viscosity model, what we do internally is that we determine first the critical volumes of each component, or you can say critical Z factors, by matching some kind of available data on the individual component viscosities at 1 atmosphere and some higher temperature with the LBC correlation. So for all, for example, C7 plus fractions, we would need some kind of estimated individual component viscosities at 1 atmosphere and some higher temperature. And that we can get, for example, from this Oriker-Bar group contribution technique. So this correlation or this technique actually gives us the viscosities that are a function of the component molecular weight and specific gravity, and those viscosities those viscosities monotonically increase with respect to the increase in the molecular weight and the specific gravity. So we match or we change the critical volumes first, that data, and this is not the measured data, of course, this is some kind of calculated data. But if you can also have some kind of measured data on individual carbon viscosities. So it's like if you are doing the TVP distillation, and that's something we discussed before, and we know that it gives us the information of individual component molecular weight, specific gravities. You can also ask for the individual component viscosities, and if you have that data, you can use that data to tune or change these values of the critical Z factors or critical volumes to match that measured data if you have it. If you don't have it, then generally you find that this correlation is reasonable for the viscosities at low pressures, and we change those critical volumes from the default values to match that data, so that the LBC model is physically consistent for the component viscosities. And after that, once we have those estimates, now we know that we have some reasonable estimates of the critical volumes. So what we have found that the LBC model with this technique, with this modified critical volumes, is generally predictive for measured oil viscosities within usually 10 to 15%. And we know that this is usually the uncertainty range for the measured viscosities. And it also ensures the physical consistency in the individual component viscosities. But after that, like after doing this exercise here, tuning the individual component critical volumes, we generally we generally try to modify the critical Z factors with only, for example, a constant multiplier or ramping multiplier to keep or like to keep this monotonicity in the individual component viscosities, so that the monotonicity is not affected. And
so, sorry, one question there. When you apply this modifier number, you apply to all the components, or you apply to the ones that have this not monotonically behavior?
No, so that like when we are saying the constant multiplier, it means all the critical Z factors of the C7 plus fractions, they are changed by the same multiplier.
Okay.
So that's why, like, and you need it because we know that the new critical Z factors that are coming from this tuning on the Oriker bar, for example, data that have ensured monotonicity in your LBC model. And if you start, for example, changing those modified critical Z factors with different sets of multipliers, then you may end up losing that monotonicity.
Okay. Okay, I see. Thanks.
Very good. So, and generally, like if we change that ZC values with the constant multiplier for all the C7 plus, for example, fraction, to measure to match better match our lab measured data, the oil viscosities or gas viscosities, we generally find that that's adequate for most studies we have. But in some studies, we also need to change very seldom the fifth and fourth degrees of the LBC correlation. And the most important thing is that whenever you start changing the LBC coefficients, then you always try to give weight factors to both the gas and the oil viscosities. We know that the gas viscosities are not generally measured, they are usually calculated, but still you should be giving the weight factor to both oil and gas viscosities when changing the LBC correlation coefficients, because the gas viscosities with correlation, for example, in a CVD test, those are not 100% accurate, but those are reasonable. And we don't want to, for example, if the gas viscosity is given as, for example, 0.0 centipoise, we don't want the LBC model to predict, for example, 0.1 centipoise in that case. That would be very wrong. So in that case, you need to have, or you need to assign the weight factors on both type of data so that you don't overtune your LBC correlation and affect the gas viscosities in a wrong manner. Yeah, so this exercise folder, you can find there is a spreadsheet on this Oriker bar correlation, which can help you finding the viscosities for individual component. One challenge in doing this exercise here that we are talking about is that normally PVT packages doesn't let you calculate the individual component properties very easily. So you need to create multiple mixtures with only one component in the mixture, and then do the flash calculation or like define the experiment on just one component to do this kind of calculating the individual component viscosity and try to match that with the data from Oriker bar. So, but FaceCom is very flexible, and we do this exercise internally. Okay, so the next topic is the QC of the EOS model. And any questions on the viscosity modeling? No.
Just a question. Yeah. Do you recommend only use LBC model? Because in, for example, in PVT SIM, you do have option, I think it was called CPC, or I don't remember exactly.
Corresponding, that's the corresponding state model. That's this Peterson model.
Okay.
Yeah. Here. Yeah, so the Peterson model, you can also use the Peterson model and like as we were saying before, that Peterson model, generally it is considered as more predictive compared to the LBC model. But and if you don't have any data, generally Peterson model is okay to use, and especially if you cannot follow the workflow that we are describing here, then you can use the Peterson model. But the workflow that we are describing here, before we found that workflow, actually what we were doing before is that we were using the Peterson model to calculate the viscosities of like, if you don't have any data, of course. So what we were doing in that case, we were calculating the viscosities with the Peterson model, and then just tuning the LBC model over the calculated viscosities from the Peterson model. Generally people prefer using LBC model in reservoir simulators because it's computationally much faster. And Curtis, do you have any comments on it?
Curtis?
Yeah, I just getting to the speaker button. Yeah, I think that the disadvantage of using the Pedersen is that there are a few software that don't include that option. That would be a disadvantage. Clearly you don't need a workflow like we're talking about here for the LBC. Workflow that's can be fairly automated if you have the right software, but most people don't use that software. So most of the PVT packages now do offer the Pedersen viscosity model, so it's it's possible to use it for modeling viscosity, and the vast majority of application software does allow you to use it. Now there are, like I said, a few that don't, and then the other thing is you have the compatibility of the tuning parameters for the Pedersen model are, I think, are not consistent from one software package to another. So we had a study recently where the company was using, I think it was PVTP with the Pedersen viscosity model, and they used, I think, 2 tuning parameters, if I remember right, for getting a match of the viscosity data. And when they wanted to import that tuned viscosity Pedersen model into, I think it was Eclipse 300, that wasn't possible. Because even though Pedersen model is in Eclipse 300, it didn't allow the modifiers used in PVTP. So what I would say about the LBC is that it has there's a uniformity of how it's been implemented across all software. Basically, you have the ZC or VCs of each component. And then you have these 5 coefficients in the 4th degree polynomial that can be adjusted as tuning parameters for, I think all software allows that set of 5 coefficients to be read in. So there's more uniformity. So those are just the issues. I'm not going to recommend one way or the other. But I think clearly probably the biggest advantage of the Pedersen method is that you I think probably get better viscosity predictions as a function of temperature than for the LBC. I haven't seen a comprehensive study on that, but the way the method works, and I suspect that you would get better viscosity predictions at different temperatures. So if you're looking for viscosities at pipeline conditions from 5 degrees C to surface temperatures and also to reservoir temperatures, then likely the Pedersen correlation would give you better temperature dependence, which can be severe. Oil viscosities almost are exponentially increasing as you go to a lower temperature. And you don't get that effect in the LVC correlation by default. So these are some of the issues without making a recommendation.
Very good. Any other questions? Okay, so the next topic we have is the equation of state model QC and quality checking the EOS model, and that's the exercise we always do when we develop a detailed equation of state model, because as we mentioned earlier that there can be different ways of going wrong in tuning the equation of state model. For example, you may have changed the binary interaction parameters too much or inconsistently, which might have caused inconsistencies in your in your equation of state model. So it's always recommended to do the quality check of the equation of state model that you like you tune to your PVT data. And so one consistency check, and the most important actually, the consistency check that you should always do on your equation of state models that when you develop is to check the consistency of the K values. And what in that case, what you can do is you can plot the K values. So most PVT packages, they can let you calculate, for example, the K values. For example, PVT-I, you can calculate K values at any pressure and temperature. In PVT-P, I think PVT-P also gives you the K values. PVT-Sim also does the same. So most PVT packages, they can let you calculate the K values, and you can export them or see them in the output files for each component at any given pressure and temperature. So you can plot, for example, K values for each component with respect to the boiling points, and here it should be. It's important to mention that if you are using, for example, boiling point on the x-axis, then these boiling points should come from the equation of state model, meaning that for each component you should calculate what is the vapor pressure, or you should give you should calculate the temperature where the vapor pressure is 14.7 psi. So that should be calculated from the EOS, and that's not very straightforward in most PVT packages. So that's why the alternative that we generally recommend is that you can plot here the K values, so Ki at TSC and K values at reservoir temperature and the standard pressure. So that's something you can also use on the x-axis. So plotting these K values, these could be at higher temperature. So for example, saturation pressure or a pressure slightly less than the saturation pressure. So you can calculate K values for any mixture you have or multiple mixtures you have in your equation of state model development. Just pick different samples, calculate the K values at reservoir temperature and saturation pressure for the different sample, and plot them versus the K values at this standard conditions, the standard pressure and the same reservoir temperature. And what you should what you should be looking in the plot, for example, is that the K values, they should be monotonically decreasing. So because we know that fundamentally the K value, if you have, for example, C1 and then you have C2, so the K value of ethane should not be higher than the K value of C1. So that's why this line or this function has to be monotonically decreasing always. So that's something you should always do after you finish the equation of state model development. And again, you can also plot the K values versus pressure, and that's how it looks like. We have seen this plot before. So it's a log-log plot. And here you can see that these are the different components, and the K values as a function of pressure, again, should not cross. So for example, this line should not go below, for example, the red line at any pressure. So this component and this component K value should not cross at any pressure. They can only they will only converge at this pressure, which will be your convergence pressure, which is again not possible in most PVT packages to calculate. So PhaseCom lets you calculate convergence pressure, and you can extrapolate all K values to the convergence pressure. But in most packages, you may be able to calculate these K values until only, for example, the saturation pressure. And also calculating the individual component viscosities and plot them versus molecular weight to see if the model is consistent, physically consistent. So this is, for example, an example of an equation of state model with only 3 C7 plus fractions, which is highly inconsistent. So this lighter fraction has very high viscosity, and these two fractions have very low viscosity, and even the heaviest fraction has lowest viscosity among these three components. This non-monotonic behavior is sometimes like it becomes an important issue. For example, if you are doing gas injection studies where you know that when the gas will be stripping off the oil, then the oil should get heavier and heavier. But in that case, when the oil gets heavier and heavier, it will be getting less viscous in your reservoir model. So that's something you want to avoid. And that's when this monotonically increasing viscosities for individual components becomes very important. Yeah, so that's something you see from like when we generally tune the LBC model. That's how, for example, the viscosities of the individual component look like versus molecular weight. If you just use the default LBC model with the default values of critical Z factors, that's how the LBC model would be predicting the individual component viscosity. And you must, yeah, and you usually, or like I have almost always seen that if you the default LBC correlation with the default values of the critical Z factors, it always underpredict your measured oil viscosities. And if you want to match that data, and if you want to have consistency in your LBC model, then the workflow that we have mentioned or recommended can be used for a physically consistent viscosity model. Yeah. So the key takeaway on this topic is that it's very easy to create a thermodynamically inconsistent EOS model that fit all your PVT data. So that's an important note here, and then that should be remembered by all people who develop equation of state models for their at their work. So. And it's always important to do a set of quality checks to ensure that the models are consistent. The equation of state model is consistent. Okay, so then the last short topic on this in this presentation is EOS model dumping. And any questions here on this topic, the EOS model consistency checks? Is there anybody? No. Okay. So yeah, so now we jump to the last topic of this presentation. That's the EOS model lumping, and the reason why we are discussing this topic is because what we recommend is that you create a detailed equation of state model first, matching all the PVT data, measured PVT data you have from all the available samples for a given field or reservoir or basin. And then you can use that equation, detailed equation of state model, for creating PVT models that can be used for different applications. And we know that for reservoir simulation, for example, we need an equation of state model with fewer components. So that detailed equation of state model can be used to consistently create different lump equation of state models, which can be used for different purposes in your reservoir model. And so that's just one slide illustrating the same concept, that like you create that parent equation of state model, the very detailed equation of state model, and then with that you can create consistently the different child PVT models, which could be, for example, a black oil or lumped equation of state model. For example, for reservoir simulation application, you can have a different lump equation of state model or different black oil table, for example, for pipe flow calculations and etc. Yeah, so what we are discussing here, that how you go from this very detailed equation of state model, XX, like 50 plus component, into a fewer component equation of state model. And again, the reason mainly is that using this detailed equation of state model, for example, for your reservoir simulation, is time consuming, and you may not need, for example, that much high resolution to accurately predict the PVT data that's relevant only for your reservoir condition. You may need a very detailed equation of state model for surface process calculation, however, where you need, for example, you need to know what are the properties of or what are the different components you are producing in your products, for example, LPG, LNG, for example, and you need to know, for example, how much benzene you are producing in your gasoline, for example. So the objective of the objective that we usually try to achieve in the pseudoization or the lumping of the detailed equation of state model is that you try to minimize the number of components that still accurately predict the PVT properties of your relevant fluids. So the accuracy of the lumped equation of state model should be very comparable with the detailed equation of state model for the PVT data that you have, or for the PVT data that's relevant for that particular application. And again, when you start lumping, then you need to know what are the objectives of that, or what are the what will be the applications of that pseudoized or lump equation of state model, and generally what components you lump are constrained by that objective. So, for example, the reservoir and process engineers, they can have usually different objectives, and then usually require different lump equation of state models. So, for example, let's say, for example, in reservoir process, you may not need to know, for example, how much LPG you are producing. So, in that case, for example, you will allow the lumping of C3 and C4 components with other components to get to a much fewer component equation of state model. But at surface, and the surface processing unit, maybe the process people are interested in those components. They may need to know how much LPG we are producing at surface. So in that case, the C3 and C4 components may not be lumped with other components, and that equation of state model will be more detailed. So these are just the different points why a process engineer may require a detailed equation of state model. And for reservoir engineers, they usually need an equation of state model with as little components as possible, but still the EOS model should give good prediction, good match of the lab data or good predictions of the processes that are relevant for reservoir conditions. So the first step in EOS lumping for a particular application is to look for such constraints and to decide which components can or cannot be lumped. And then once you know those constraints, then ideally what you should try to do is you should try all the possible combination of the different components that can be lumped together and see which combination gives you the best results compared to the measured data or compared to the data that is predicted by your detailed equation of state model. Yeah. So this point here, the possible combination that you should try all the possible combination of the different components. That's the key thing in the workflow that we use, for example, internally to come up with a detailed equation of state model. Oh, sorry, the lump equation of state model, and that's described in this paper. In this paper here. Curtis, do you want to add a few cents on it, like why you decide, like why you wrote this paper, and just a few points on the history?
Well, if you look at the kind of the short and the long list of papers talking about component lumping, probably the first one is, I think it's the 1983 or 85 paper by Coates on simulating gas condensate reservoirs. I think that's one of the papers we'll probably provide part of the course. And it gives a comprehensive discussion of how to do and can use lumped EOS versus detailed EOS. So that paper by Coates, simulating gas condensate reservoirs, is a good starting point. The problem in that paper is that you're not guided towards which components to lump together. What's the strategy for that? In the 80s, 90s, and probably into the 2010 period, there was a lot of different papers. A guy named Lee Bavici, some people at DTU, Steinby, a few others, CMG, myself in the monograph, and also in the original paper in 1980, talk about heuristic strategies for selecting which components to lump together. Okay, I'm going to try something here that's a bit spooky for me. Can you all see me? Yeah. Anyway, so those papers lines are be conclusively the best. The PVT sim algorithm is on the C7 plus. They basically, each of the 11 C7 plus fractions they have has approximately the same mass fraction. So they do this detailed this detailed splitting, I think, out to C80, and then they do lumping back to 11 fractions, each with approximately the same mass fraction. There's a lot of heuristic, and people maybe claim theirs is the best, but when teaching this course through the years, I never felt comfortable in this part of the discussion about lumping, and it's so important. What I did know is that depending on what process you were going to simulate with the equation of state, the lumped equation of state, the lumping, the set of lumping components might differ. If it's pure depletion, you might get away with 3 C7 plus components, for example, like coach suggested. If it was first contact miscibility, you might get away with 3 C7 plus components. If it was multi-contact miscibility, you might need 5, and which components you need. So it would be depending on the process that you're going to be using that equation of state to simulate. That I think is very important, and nobody really talked about that. So it was always frustrating to discuss this topic because there was not really a good set of guidelines. You just had to trial and error as best you could, or just push the button that the software you were using gave you as an option to do lumping. And so when we got back from teaching the course, we sat down together, a few of us at the company, and decided I wanted to find out how many combinations, how many, acceptable combinations. For example, that the components you group together are, what do they call it, next to each other. So like you don't mix C7 with C36 plus, so basically there's a limited number of combinations. Why don't we just try them all in some kind of automated manner? So that was the idea, roughly. And then Ahmad Lavian and Cecil Martinson basically started on the work of actually trying to look at all of the feasible combinations to see how long it would take to make that run. And each time we would do a new combination of lumpings to let's say 11 pseudocomponents. We would compare it with all the other combinations that would go to 11 pseudocomponents. And we came up with some metrics for how to choose which one was best, et cetera, et cetera. So that's what led to the paper that we found out that you could do within usually about a 24-hour period. So there were a lot of runs. There was hundreds of thousands, if not tens of thousands, 100,000s of cases, and you basically just ran them all, and you had these metrics, and you picked the top 10 with the best metrics. And then you would look in the details of how the comparison of the detailed EOS was with these top 10 lumping strategies. And then you would finally have to pick one or maybe a couple of those and give to the client to use for their simulation. So that's what we've been using since the paper was written. I don't remember the year, but it was between 2010 and 15 maybe, I don't remember. And it basically it does two things. It takes the guessing work or the heuristics out of which group of components to use, and it allows you to create a PVT data set that reflects the processes that you're going to be simulating using that equation of state with. So it handles those two main problems, is which groupings you let the statistics tell you, and what process you're going to simulate. You can create this PVT data. So 2014 was the year. So this in my opinion was a go-to method. The problem was that it took a long time to run. Now recently there was a couple of things that happened subsequent to this. One of our colleagues, associates at Whitson, Arnold Hoffman, has published a new paper and developed even further after that. So methods that allow you to do what took 24 hours before. I'm going to turn this. The video doesn't seem to be working well, so I'll turn that off. So it didn't take 24 hours. It would take 10 minutes. I don't understand all the details of how it works, 10 minutes to 30 minutes, but basically much, much faster. And it also gave you some additional advantages. So that's some new developments, and we use that strategy better today. I saw a recent LinkedIn post by Mark Santos. Mark, I can never pronounce his last name.
Right.
Yeah, and we might give a link to that to the people. And he just took the paper and he went in and he coded it up in Python, I believe. I think he uses FaceComp in the launches of testing all the different lumpings, but he gives his he basically says, I just went in and programmed it up and it worked. I don't remember the details, so it's not like it can't be done, but you probably can't use most of the softwares because you have to be able to launch your PVT software as a, what do you call it, as a executable. I mean, kind of like a DLL or so there's not too many softwares that you can actually do this with. But to me, at the end of the day, you can say, well, instead of speculating about what combination and lumping is best, without randomly having it predict a few saturation pressures, I don't know how that does it, you know, randomly choosing the PVT data it's going to try to honor. You have total control over the data that you're setting up to simulate, the processes that you want to simulate, and you let the mathematics, the statistics find out what is the best set or the best lumping scheme. That's the short story behind the methodology that's in this paper, and I think it's a good one. I think it takes the guesswork out, takes the speculation out, and does a great job. So and particularly the later improvements are on instead of looking at all of the possibilities, he uses some methods to sub-select which ones to look for, and apparently it's very certain to give you the best had you looked at all of them. So I don't know how it works, but it works very well and it works very fast. So that's pretty much all my comments. I don't know if there's any questions or comments, Bilal, you have.
Yeah, just a quick comment on Arno's paper. So he actually uses an optimization algorithm. That's a genetic algorithm together with a taboo search to find out, as Curry said, to find out the subset of the combination that needs to be searched for, to find out the best combination actually. So we can also include that paper actually in this in the papers list. Any questions?
Yeah, so I think the two advantages, one other advantage that I didn't mention is that it allows you to find the fewest number of lumped components that give you a certain metric of quality. Yeah. And because when you go into a study like this, you don't know if it's going to be 11 or 4.
Yeah.
So it also gives you a relatively fast way to find out, can I live with 6 pseudo components total or not? And what's the metric if I do 6 components and it finds the best 6 components? How bad is it? Maybe you're willing to live with it because of a runtime issue.
Yeah, that's exactly right. Yeah. Okay. Yeah. Okay. So the key takeaway on this topic is that the different again the different petroleum engineering calculation, for example, the reservoir simulation, pipe flow or process calculation may require PVT models with different resolution, and it's always recommended to first develop a detailed equation of state model that you can use to generate the different child PVT models in a consistent way. So with this, we finished this presentation, and after this, we will jump to the EOS model applications again, see what are the different applications, and just focus on some of them.